today's challenging environment, scientists and engineers need to accelerate discovery processes. CAMECA offers unique, high-performance analytical instruments to help them unveil the secrets of life and materials at the micro, nano, and even the atomic scale. Founded near Paris in 1929, CAMECA rapidly established its name by pioneering first electron probe microanalysis, followed by secondary ion mass spectrometry, and more recently, atom probe tomography. Ever since, we've maintained our R&D investments at their highest level and partnered with leading academic institutions in order to explore new techniques and technologies. Today, CAMECA is part of the Materials Analysis Division of AMETEK, a global manufacturer of electronic instruments and electromechanical products. We have locations all around the world and strive to expand our reach to new geographical frontiers in order to foster emerging scientific players. Our state-of-the-art production facilities in France and the US allow our experts to develop the most sophisticated microanalytical tools used for research and process control applications in materials, semiconductors, geology, environmental and life sciences. Huge investments are made worldwide towards the development of stronger, lighter and more durable materials for transportation, energy production, aerospace and defense, and consumer products. Materials scientists rely on CAMECA instruments not only to gain a deeper understanding of the properties of materials, but also to predict their performance in real world. CAMECA also accompanies semiconductor manufacturers as they explore the boundaries of physics. Our metrology tools enable the production of latest generation electronic devices, contributing to a world where communication is faster and more reliable. From understanding the microstructures of rocks and the genesis of the solar system to revealing water and soil pollution processes, CAMECA provides the tools for writing the history of the universe and creating a safer environment. Offering novel and powerful instruments for studying intra- and transcellular metabolic pathways, DNA expression, virus penetration, and drug localization, CAMECA enables important medical advancements. Thanks to such a wide spectrum of applications, our instruments have been adopted by top-ranking academic and research institutions, as well as major industrial corporations all over the world. Their satisfaction and success are our main focus. The expertise and passion of our teams will enable us to further push the limits of microanalytical instrumentation and help our customers reach the highest performance in their specialized fields. CAMECA, Science and Metrology Solutions.
Atom probe tomography. It's the only material analysis technique that offers both 3D imaging and composition measurements at the atomic scale, and it's controlled.
Good morning. Today's chair will be David Sexy. David, can you turn on your speaker? Yes. Okay. Over to you. Yes. Good. Okay.
Yeah. Thank you, gang. Yeah. Good morning and welcome to day 3 of the program. My name is David Sexy and I'll be chairing this 7th technical session this morning. We have some great speakers coming up in the next 4 talks. Thank you to Gang again and all of the other organisers for the meeting so far. It's been really good and it's a pleasure to be able to chair this session this morning, so thank you for that. Just for each of the speakers, I've just planned to give you a 2-minute warning towards the end of your time, and we'll try to keep to time as much as we can in this session. So without doing anything else, I'm just going to introduce the first speaker this morning, which is for an invited talk. Our speaker is Dr. Day3, and he is a Research Associate Professor of Material Science and Engineering at Northwestern University, and he manages the Northwestern University Centre for Atom Probe Tomography. Now, after receiving a doctorate in physics and physical metallurgy from the University of Göttingen in Germany in '95, Dieter joined Northwestern University for postdoctoral studies in 1996 and was reappointed at Northwestern in the rank of research faculty in 2002. His research interests include phase transformations in solids, nanostructured materials, structure and local composition of interfaces in materials, and structure property relationships of materials. He specialises in high-resolution atomic scale materials characterization and analysis, with a focus on atom probe tomography, and he has published more than 150 research papers. So welcome Dieter this morning to give his presentation to us. Thank you, Dieter.
Well, thank you for the introduction, David. Just confirming, do we have sound? Can you hear me?
Yeah.
Oh, that's great. Yeah, and so thank you to the conference organizers and Gang Shah specifically for putting together this virtual conference and for bringing everyone together into a virtual room, if nothing else. Thank you for that. So I will try to share my screen. I believe, let me see, I may need permission. Oh, I can. Oh, okay. It works out of. Okay, this looks good. Great. Just let me move this out of the way. And let me get my laser pointer. All right, thank you very much again for the introduction. My name is Dieter Isheim. David just introduced me and it's a pleasure for me to talk a little bit about the proxygram, which is a frequently used data analysis tool available in many of our software packages. It has been in use now for more than 20 years, and I'm happy to give a brief review about how this came about and what we use it today. I want to thank you especially to Olaf Hellman, who is at Microsoft now, who basically led the efforts to develop the proxygram over 20 years ago, and special thanks to David Seidman for being our center director and leading many research efforts we have been involved in. The thank yous extend also to many current and former members of our research group and collaborators that contributed in many little and large ways, be just a conversation pointing to a good research topic, providing a sample, or just many of the little things that happen at a laboratory every day. So I won't embark in reading the list. we also have to acknowledge support from funding agencies, specifically to the Office of Naval Research and the National Science Foundation. They basically gave us the money for our instrumentation and supported many of our research projects. So now let's get started. It doesn't need much reminder that what keeps us going in atom probe tomography is the outstanding spatio-compositional resolution. This is really unique to atom probe tomography. And this talk is one contribution to essentially getting the best results out of the data our instrumentation provides us with. I want to point out that frequently we're looking at elemental compositions, but atom probe excels as well as isotopic resolution, which has become the subject of a lot of studies more and more recently. So the isotopic analysis option of atom probe tomography is an important addition. We all know that in atom probe tomography, the ultimate limit for what we can see in terms of composition, it comes down to atomic counts. Every one atom is important, and putting the atomic resolution and single atom sensitivity of atom probe to some good use is not necessarily trivial. And much of the software we are dealing with is built around just around that. This leads us straight into a topic. We have atomic resolution, but there is only that many atoms. Typically, it is about 40 to 60 per nanometer cube. And that means the closer we look, the fewer atoms we have, and the counting statistics breaks down frequently. And now one way to overcome that is keeping an eye on selecting and optimizing region of interests. This sometimes is also referred to as a segmentation of a data set. It is basically breaking down the data set in volumes that carry equal or similar information, so that in combination we can improve the statistics. Similarly, we can use a volume decomposition or region of interest, ROI selection, which are very important tools for our data sets. I'm frequently tempted also to work with a data set as a whole, but from experience, I want to emphasize that suitable segmentation cuts your data set down to whatever gives you the most useful results. This leads me to commenting that we all know that the atomistic data in our data sets is extremely complex. The information by having millions or hundreds of millions of atoms in 3D space is very rich. And in our field, we have more and more the recognition that it is actually the software that gives us the results. And I heard multiple times the mentioning of that the software is the actual microscope. And I think in preparation of talking about the proxygram as a data analysis method, I can wholeheartedly underwrite that statement. I wanted to briefly recap a history of how did we end up with that analysis functionality called proximity histogram, or proxygram for short. Now it all goes back to the invention of a three-dimensional atom probe beginning in the late 1980s, specifically the practical instrumentation from the group in Oxford, the POSAP, and the group in Rouen, the tomographic atom probe. And pretty soon, isosurfaces had been adopted as a visualization tool, and it was pretty much inherited from software for three-dimensional computer graphics. And what basically happened is a concentration grid was calculated with with the voxelation, and from the concentration grid with the Marching Q algorithm, using triangulated meshes, a set of triangulated meshes, isosurfaces were calculated, and that was a very convincing way of getting a visual idea of what are the chemical features in a data set. Now, after having found that an isosurface can be really representative of the microstructural feature in the data set, the next and critical step was, what are potential ways of using that as an analysis tool to get data out of it, in addition to a mere visualization? If you look at something and it's beautiful, my bet is that there is a deeper meaning into that. And in atom probe tomography, this is a prompt to use ISO concentration surfaces in addition to visualization and making pretty images to use that for a quantitative evaluation. And this is where Olaf Hellman and a team, including myself, started in about 1999. This was the early phase when we had three-dimensional data. And so this became important very quickly. And since we were looking at interfaces and Gibbsian interfacial excesses at the time, the initial goal was creating a useful method for measuring the Gibbsian interfacial excess at arbitrary interfaces. This is the initial driving force for the proximity histogram. And then later on, after we worked with it for a while, we started using the proxygram also for measuring phase compositions and in a more general sense, measuring compositional variations in the proximity of interfaces. The basic ideas of the proxygram are summarized in a key publication by Olaf Hellman in Microscopy and Microanalysis in 2000. That's a typo. That should be 2000, volume 6. And Olaf implemented the proxygram first in a custom-made application software package called ADAM, which is short for Atom Probe Data Manipulation, which was described in a publication referenced below in Material Science and Engineering in 2002. And Olaf kept developing the software, and many of the functionalities are now in an application called Apex. And I believe this is my next slide. Yeah, Olaf is still active and maintains a website called Tomographic Softworks. It's a little bit like a blog, but Olaf is interested in hearing from the current developments in atom probe tomography and keeps developing his atom probe software. He is a link how to get in touch with Olaf. Now, this is the key publication I wanted to introduce with the correct year. This was published in 2000, Microscopy and Microanalysis, with the title Analysis of Three-Dimensional Atom Probe Data by the Proximity Histogram. Olaf is the first author and leading force, and the rest of us, we are proud to contribute to the effort. I just want to point out in the abstract, it's funny to read this after 20 years. It says the number of atoms collected can be on the order of 1 million, representing an analysis volume of approximately 20 by 20 by 200 nanometers. This large amount of data allows for the identification of microstructural features and so on. It's really interesting to see in retrospective. Of course, this was before the introduction of the local electrode atom probe. In the meanwhile, the typical size of a data set in APT is at least in the 10th, if not hundreds of millions of atoms. So this is the difference of just a couple of years looked at now after 20 years distance. This article outlines a data compilation technique for the generation of composition profiles in the vicinity of interfaces in a geometrically independent way. The latter is important because composition profiles up to that point used to be created with a one-dimensional cylinder, and operating a cylindrical probe in 3 dimensions, whoever had done it is quite a challenge manually. And the proxygram essentially does not require manually placing a cylindrical probe or anything. And on top of that, it can measure composition profiles in a much more generalized way than what the traditional one-dimensional concentration profile with a cylinder does. The proxygram received a somewhat hesitant, but over time, very positive acceptance. This is the number of publications referencing Olaf's paper in microscopy and microanalysis. So the first couple of years, there wasn't all that much use of it. The breakthrough was related to when the proxygram became available in IVAS. I believe that was IVAS version 2 around 2006. And then the use of the proxygram dramatically increased. So we are seeing about 50 publications plus per year for which the proxygram has become an integral way of data evaluation. I'm moving on to explain a couple of the basic ideas. Trivial, but worthwhile mentioning is the name proxygram is short for proximity histogram. This is also the reason why it spells with an I. It's not a proxy, but it is a proximity histogram. The name is the program essentially. The algorithm measures the distance of every atom relative to proximity to a two-dimensional surface, and then it creates a histogram with respect to distance from that interface for all the atoms encountered. And the concentration profile is then generated by simply normalizing the counts in the histogram bins with the total number of atoms in each bin. This is the way a concentration profile is calculated, which of course is then with respect to distance from a surface or a given set of vertices that come from the marching cube algorithm used to approximate, to interpolate the interface through the concentration space. I want to emphasize that any two-dimensional object that can be represented by a set of vertices can be used as the basis for a proxygram. Most commonly, we are using an isosurface. This can still be an isosurface relating to density, to atomic concentration, to ionic concentration, or a lot of different isosurfaces. Most commonly, we use an isoconcentration surface because that's relatively easy to understand. The quantities typically evaluated with a proxygram, I mentioned already, starting out with measuring Gibbsian interfacial excesses. We have used the proxygram to determine phase compositions. This is very efficient if you get into the far field, far away from the interface. So in this sense, the proxygram is not simply a tool for analyzing an interface, but we also want to look into the far field at a further away from the interface, and can then measuring phase compositions. Of course, any gradients across the interface are also included in this type of profile. And in addition to interfacial excesses, which we mentioned already, generally at interfaces, there are funny things going on. The proxygram picks up all of those. In this way of looking at a microstructure, I want to emphasize that we have not abandoned, but we did not use the idea of looking at a given 2 or 3 phase structure. The good news in that is that we are not making any assumptions. The challenge is if we later on trying to make this compatible with any models that are based on a simple 2-phase system, we cannot easily use things like the lever rule or anything that implicitly makes use that you can have only 2 phases and a sharp interface in between. So in that regard, the proxygram is a very general tool, we need later on to make an interpretation of the data to make it compatible with the ideas we have about what a microstructure should look like. I want to comment a little bit about using isosurfaces for thresholding, because that is a question that's frequently asked. So an isosurface, in all generality, is a very useful tool to binarize a 3D point cloud by concentration. Just there is a volume where the concentration is higher than X, and what usually is outside of that interface, the concentration of X is less than that. So in a way, we are binarizing the data set into in and out. In that way, the isosurface is a great tool to locate a gradient. However, if you're just looking at a single isosurface, it's not telling us much about what the gradient looks like, how much is it going up, how steep is it. It just tells us there is a gradient. Now, this is exactly where the proxygram kicks in. The proxygram measures the gradient and tells us pretty much everything composition-wise that's going on across the interface. This means we can use the proxygram to first learn something about the compositional gradients across the interface, and then we can use the results in an iterative way. Once we know how that interface behaves, we can refine the thresholding. So the thresholding is nothing magic that somehow it falls out of the sky, but the proxygram can be used in an iterative way to investigate a concentration gradient and then pick a thresholding value that serves us best. Great. The next slide is now a little explanation of how the algorithm works. For simplicity, on the left side, I drew a 2-phase structure with red atoms and blue atoms. The red atoms are segregated into a precipitate. The precipitate has a surface, and just for simplicity, I chose a 50% red isoconcentration surface that outlines the precipitate. Notice that I could have chosen a different threshold. It would just switch over to one of the black lines, and I would just have ended up with a different origin for where the proxygram starts. Now, the proxygram starts by taking each individual atoms and measuring the distance from the isoconcentration surface, that's the red line here. After determining the distance, it puts all atoms into bins. These are these shells that envelop the precipitate and go in. And by dividing by the number of atoms in each shell, we can calculate a concentration. And on the right side is the proxygram concentration profile that would result in that case. So we see the isoconcentration surface is the origin of the proxygram. And on the left side are the bins into the blue-rich phase, and on the right side is the red phase, which in this case is 100%. And I threw in a couple of green atoms at the interface, which show up as a bump in the concentration at the interface. So this is how we can measure interfacial segregation, how we can measure concentration gradients across the interface. And it is clear in the far field, if we go out far enough, the flat part of the proxygram tells us about the phase composition. Now we are going to put that to some good use. Here's my first example. It is a nickel-based model superalloy with 4 components. It is ruthenium, not rhenium. Sorry about the typo. On the left side is the microstructural evolution. We age at 700 degrees Celsius for various times. And in the middle is the proxygram concentration profile after 256 hours. It has the features I described before. On the positive distances from the precipitate, from the isosurface distance, we have the gamma prime precipitate, which is rich in aluminum. And in this case, we measured the plateau compositions, determined the phase compositions, and we chose a threshold at the mean concentration, which comes out to 12.9 atomic percent aluminum. So that's the reason for this odd value. And the sigmoidal concentration profile is symmetric. And this means at the halfway point between matrix and precipitate composition, it automatically lines up with the inflection point of the sigmoidal concentration profile. And this has the advantage that this is the area where the isosurface is the most self-similar against small variations of the concentration. And you can see, even if we varied the concentration a little bit up and down, close to the inflection point where the concentration gradient is the steepest, it has the least influence on the position of the interface. So this is one strategy of picking a concentration threshold for the proxygram, and it is reiterating on the iterative use. Once we know the concentration gradient across the interface, that can be helpful for choosing the threshold value. I also want to point out that the gradients, they look a little bit different, and in fact, the composition, the interfacial width is different for different elements. This is one result, and the proxygram has been used to measure interfacial width. It doesn't need to be the same for all elements. Interfaces can be very complex features composition-wise. My next example is also for a nickel-based superalloy. Now, in this case, the sample was cooled continuously at a rate of 25 degrees Celsius per minute from 1150 degrees Celsius. And as the sample cools, there's multiple generations of gamma prime precipitates forming. As you keep cooling, you're building up additional supersaturation. On the top left of the reconstruction here is the so-called secondary gamma precipitate, which formed at a higher temperature and is larger. And then as you cool down and build up supersaturation, you get an entirely new generation of tertiary precipitates. And we use the proxygram method to analyzing these precipitates. If we start with the tertiary precipitates, it looks pretty much like before. We have flat parts in the far field concentration. The proxygram gets a little bit more rugged at the end as we approach the inner parts of the largest tertiary precipitates. That's just where counting statistics break down because we are running out of atoms to look at. And we can safely measuring phase compositions. The secondary precipitates are much more interesting because it turns out the proxygram doesn't show a plateau, but as we cool down and the precipitates put on additional layers of material, and the composition changes as the thermodynamic changes with temperature. In this specific case, at a lower temperature, the new layers added to the secondary precipitates are more rich in aluminum and less rich in titanium. And the outermost layers of the secondary precipitates have almost the same composition as what we see in the tertiary precipitates. So in this way, the proxygram becomes a tool to track the evolution of precipitates with changing the temperature. And of course, this can all be put into thermodynamic and kinetic databases measuring diffusion as the thermodynamic changes. My next example is about copper-rich precipitates in a model steel. Now I'm showing the proxygram here because it's a little bit of odd. It doesn't show, we were looking for copper-rich precipitates. The goal of this work was simply to demonstrate we could do precipitation hardening also in a non-magnetic austenitic steel. So the proxygram here, it doesn't have a plateau, and in fact it has a little bit of a bump here. Now this is an indication that the proxygram is telling us more than a simple two-phase situation, because we have precipitates of varying size, and the composition of copper precipitates in iron, that's a whole story on its own. I can't go into much detail here, but the proxygram is telling us that we probably have more than the simple situation of one type of copper precipitates with a final composition. In addition, we can also see a little bit of segregation of nickel and manganese to the surface.
2 minutes, Dieter.
Thank you. My next example is also a steel, and I need to skip ahead. I wanted to talk a little bit about the segmentation process. This steel has a very complex microstructure with austenite, martensite, copper-rich precipitates, and carbide precipitates. In terms of, if you look at it through isoconcentration surface, it's much easier to see. The green isosurface separates the nickel, the red is the copper precipitates, and black is carbide precipitates. And so we can now study the austenite martensite interface by removing the copper and carbide precipitates, and we get a proxygram that shows us the phase composition in the far field in the austenite and the martensite. And what we were particularly interested in here is the enrichment of nickel and manganese close to the interface, and the interfacial segregation of chromium, carbon, molybdenum, and silicon. And the next slide is dedicated to looking at impurity elements. So by bundling up the information from the data set along the entire interface, we are able to picking up segregation of phosphorus and boron at about a 100 ppm level. This could not be done by anything less sophisticated. My next to last example is the proxygram analysis of a grain boundary in samarium-doped ceria, which is an ionic conductor. And in this case, it was supposed to be high purity ceria doped with 2 cation % samarium, but it turns out there is ppm level impurities of aluminum, silicon, calcium, magnesium, and a couple of more elements which all deteriorate the transport properties. And with the proxygram analysis, we were able to characterize the composition of the grain boundary and develop a better understanding of the conducting properties here. I want to give a brief outlook. I really liked, there was a paper by Peter Felver and Julie Kearney a couple of years ago that generalized a use of the proxygram. And basically what they did is they generalized the proxygram in the sense that you can go in and select, given a certain criterion, certain parts of an interface, and based on that subset of triangles, you can create local proxygrams. And in this way, they were able to show that there is a bump of niobium at the surfaces at the surface areas in this part of the picture, whereas the niobium concentration was pretty much flat in the the other areas of that interface. So this is a really nice generalization on how use of the proxygram can be refined. I'm coming to I wanted to also point out that Peter Felfer has many of his MATLAB scripts as part of a MATLAB toolbox on GitHub. So I encourage everyone to check that out. And I want to summarize that the proxygram developed early on after we had three-dimensional atom probe data has been seen a lot of applications in the past 20 years. I showed a couple of application examples, and I'm happy to see that it is widely used, and there even has been ways to put a more general angle added and also use it in other fields. Thank you very much for your attention, and I'm happy to take a question or two.
Yeah, thank you very much, Dieter. That was really good. It's I must say possibly the most widely used software tool for atom probe data analysis, and yeah, it does that job of taking it from visualization to quantification, which is so important. So thank you for that. I think we better move on just for now. So if anyone has any questions for Dieter, as indeed I do, just maybe we can handle that through the chat or email afterwards. So thank you, Dieter.
Thank you, David.
Okay, so our next speaker this morning is Sandra Taylor. So if Sandy, you're available, and Dieter, you might need to, oh, you've stopped sharing your screen?
I did stop sharing.
Yeah.
So it should be,
okay,
channel should be free.
Okay.
All right, can you hear me?
Yes, thank you, Sandy.
Okay, great. All right, thanks, David, and to the conference organizers for putting on this event. My name is Sandra Taylor, and today I'm going to talk to you about how we've applied atom probe tomography to understand oxygen transport pathways in metal perovskite heterostructures of interest for catalysis applications. So, okay. Move forward. And first, I'd just like to thank all my collaborators on this project, especially Kayla Yano, who helped me and was a huge contributor to the work that was performed here, as well as Liz and Sten and Dan for their contributions to the APT analysis. I'd also like to acknowledge our funding sources, being the Chemical Dynamics Initiative here at PNL, and EMSL for providing the facilities and equipment for this research. So to start off with, perovskites are perovskite structured transition metal oxides, have this general chemical formula of AbO3, and are broadly used for catalytic applications from photocatalysis to solid oxide fuel cells. They have the unique ability to accommodate a variety of dopants that in turn affect the redox properties in the material as well as the defect content, where as an example, this lanthanum ferrite can accommodate strontium in the lanthanum sites, which in turn leads to iron being partially oxidized, as well as the formation of oxygen vacancies. In turn, oxygen mobility in these perovskites is also important to their reactivity and functionality as catalysts, where in particular, due to the high vacancy concentration within these materials, oxygen can experience really fast diffusion. It could also experience oxygen exchange as well. And so the sequence of how oxygen exchange proceeds in these systems involves a number of elementary steps, from oxygen absorbing on the surface to an oxygen in the material leaving. So there is a number of reaction sequences that are involved, but this process isn't still fully understood yet. So it's of interest to understand oxygen mobility in these materials. Additionally, when you think about the application of these materials within electrochemical cells, such as those that are being considered for solid oxide fuel cell applications, the ion transport would be further complicated by synergistic reactions with the components in the cell. For instance, at high operating temperatures used for solid oxide fuel cells, metal interconnects can cause the cathode material, which is the perovskite, to degrade in performance. And this is caused by a phenomenon known as chromium poisoning, where in general, chromium from the interconnect can deposit on the cathode and in turn reduce its operating capabilities. And so it's important to understand oxygen mobility across these phases as well to get an idea as to how within these electrochemical cells, the different components can affect oxygen mobility, and in turn how that would affect cell degradation, or perhaps we can design ways to optimize the cathode performance. So in this study, the objective was to resolve oxygen transport pathways through a metal perovskite heterostructure using isotopic tracers, where the material we used is a lanthanum ferrite film, epitaxially grown on a lanthanum, strontium, aluminum, tantalum oxide, referred to as LSAT. We also deposited nickel and chromium metal layers on top of the LSFO film to model their interaction with a metallic interconnect. In order to probe oxygen transport within these materials, we made them into APT specimens and annealed them using our in situ reactor setup in an oxygen gas, where in this case, the oxygen is isotopically enriched in APT&O, while the specimen is at natural abundance. So that means that it's the 16O oxygen isotope is dominant. And so first, to highlight the baseline characterization for this sample, I'm showing here that the as-grown specimen, we can observe distinct phases in our particular geometry, being the nickel and chromium metal layers overlying the LSFO and LSAT. And additionally, we confirm that the oxygen isotopic composition in this material is effectively at natural abundance, so just very low fractions of APT&O. After annealing in APT&O, we see that the specimen has changed both in its elemental and oxygen isotopic composition, where in general, we show that oxidation and oxygen exchange reactions have occurred across this metal perovskite structure, where moving from the nickel down to the LSAT base, we see that the nickel has oxidized and transformed to nickel oxide, which is we're able to tell based on the oxygen concentration profile and comparing it to our baseline specimen. We see that the chromium has oxidized, but interestingly, it's mostly at interfaces with the neighboring phases. So for instance, we have chrome oxide near the nickel interface, as well as near the LSFO interface, but the bulk has remained largely metallic. And LSFO has not changed elementally, but what we actually see is that the oxygen isotopic composition has changed significantly, where it went from being APT&O depleted to now being almost entirely composed of APT&O. So this suggests that the LSFO underwent near complete oxygen exchange. And lastly, the LSAT, which is also a perovskite structure, but has less oxygen vacancies in it, seems to have not changed elementally or in its oxygen isotopic composition. So this shows that it's inert. So within this one specimen, we're capturing a variety of different reactions that suggest that oxidation of the metal layers has occurred and oxygen exchange of the perovskite has occurred. the LSFO specifically. So to dig into these particular reactions, we did additional analyses where, in particular, to understand energetic drivers or barriers for oxygen exchange in the LSFO substrate, we used atomistic modeling to understand how oxygen is mediated by the high vacancy content in these materials. And what we found from these results is that the extent of oxygen exchange in our system appears to be reasonable because there seem to be a few energetic drivers for oxygen exchange. One of them being that with increasing temperature, where our reactions were conducted at 400 degrees C or 670 degrees Kelvin, that the vacancies become more unstable, and thus this could facilitate oxygen exchange within the system. Additionally, we also see that there's an isotopic effect, where if you were to compare the energetics between LSFO composed of the 16O isotope with the LSFO composed of the 18O isotope, we actually see that at the temperatures that our experiments were done at, that it's more energetically favorable for the LSFO to exist with the 18O fraction. So this shows a couple energetic drivers as to why oxygen exchange occurs so readily within the LSFO. But interestingly, there are also energetic barriers, particularly for vacancy migration, where, for instance, you have to overcome an energetic barrier in order for an oxygen vacancy to migrate across the perovskite cell, and so that kind of works against oxygen exchange being able to occur. But it's likely that the high concentration of vacancies within the system are able to overcome this energetic barrier for vacancy migration, and that the reaction is controlled largely by fast oxygen diffusion. So having understood a bit more why oxygen exchange occurs in the LSFO, we also wanted to probe the oxidation within the metallic layers, being the nickel and chrome, where when we look at the distribution of the 18O across the nickel and chrome layers, we start to see that that oxidation occurs by different pathways. Where, for instance, if you look at our nickel layer, you'll see that it is largely composed of 18O. So this suggests that the metallic nickel was oxidized by 18O from the chamber. Versus if you look at the chrome oxide at the interfaces, you'll see that it's more subtle. There's actually this gradient in your 18O concentration where it's highest in 18O near your neighboring phases, but then moving towards the chromium bulk, it's actually more 16O dominated. So this in turn suggests that chromium in the interior of the tip is not being oxidized so much by the 18O from the chamber, but that the chromium is actually pulling oxygen from the neighboring phases, and that's why the interfaces are oxidizing specifically. So from this study, we're able to resolve a variety of oxidation transport pathways where we're capturing oxygen exchange within the LSFO and nothing happens in the LSAT. We're also capturing oxidation of the nickel and chrome, where they appear to proceed by different reaction mechanisms, where the nickel is oxidized by oxygen from the chamber versus chromium is oxidized by pulling oxygen from its neighboring phases. And so through this study, we're able to capture diverse oxygen reactions and transport pathways that were uniquely enabled by APT's ability to resolve isotopic tracers. And so in turn, we believe that this technique can be applied more broadly to understand the role of chemistry and microstructure across various novel materials, to understand how oxygen transport would affect their reactivity and functionality. So with that, I would like to thank you for your attention, and I can take any questions.
Yeah, thank you, Sandra. That was really good. Great example of, again, using Atom Probe for isotopic tracing. Does anyone have any questions? Sandra, probably have time for one question. Oh, I can't see anyone, or you can speak up. I just have one question, maybe, Sandy. I saw you mentioned about an isotopic effect. I didn't catch exactly what that was. Was that, I mean, do you see any mass-dependent isotopic effect, or is it a different effect that you're talking about?
Yeah, so from our calculations, it suggests that the higher mass of the APT&M oxygen leads to a higher entropy in the system. And so then in turn, that leads to a more energetically favorable state.
Okay, yeah, interesting. Okay, well, thank you again, Sandra. And
All right. Thank you.
with that, we'll move on. Okay, so our next speaker this morning is Pamela Pineda-Dominguez. And so I'll invite Pamela to share her screen and begin when you're ready.
Yeah, sure. Hello, good morning to all.
Invite Florian to share your screen and begin your presentation.
Thank you very much, David, for the introduction. Let me share my screen real quick. Okay, you should be seeing the title slide right now. Is that okay?
Yeah, that's good.
Okay. First of all, thank you very much to Gangsha, Wuyan, and Huili for this warm welcome in the Atom Probe community in China, where I'm located right now. And also big thank you to Gangsha and the organizing committee of this conference for giving me the opportunity to be involved. That's very nice. Today, I'd like to speak a little bit about how we were trying to find out what is aluminum actually doing in zinc oxide thin films. So let me go over the content real quick. I'll introduce zinc oxide and the use of it a bit. I'll go over what we did, what we found, and more specifically into interfacial access analysis, multi-domain clustering, and then I'll present the conclusions in the end. So where do we use zinc oxide? Zinc oxide is one of the main uses is as a transparent conductive electrode or for flexible electrodes in flat panel displays, solar cells. And here's a nice example of a electrochromic window where I was on a flight to Shanghai some time ago, and I couldn't figure out how to make the window darker until I found this button, and then I realized this button actually apparently applies a voltage to the window, and in this way triggers an effect that lowers the transmissivity. And this is a perfect example where we would need a transparent conductive film or layer on something in order to distribute a voltage or a potential. And so why do research on aluminum doped zinc oxide? The overall goal is to reduce the resistivity of doped zinc oxide, increase the mobility of charge carriers and their concentration. So we either dope it with aluminum or other elements in order to change the electric properties, make it more or less accepting of electrons. But the problem is that a too large concentration of free charge carriers can actually shift the plasma frequency. So there's quite a limit. And also, this then leads to the task that it's probably better to try and figure out ways how to increase the mobility. And the mobility of charge carriers is essentially limited by scattering. And there are two types. There's one type of scattering which physicists look at, which is the intrinsic scattering due to the band structure. And then there's extrinsic scattering, where which is probably what material scientists using atom probes look at, which is caused by dopants, their distribution, charge carriers, and grain boundaries. And so what we did is we wanted to know, how is the aluminum really distributed in the layer? Is there any clustering, and if so, where? And in order to achieve this, we prepared zinc oxide thin film through magnetron sputtering. And we looked at two conditions, as deposited condition and also an age condition, where we promoted the processes in order to speed up things a little bit and see what could be a more extreme condition. We're using FIB for sample preparation, a TM to look at microstructure, grain size, and texture in these things. And the atom probe instrument we used was a LEAP 5000 straight flight path instrument. And so here are some of the results from the TEM precision enhanced diffraction study. We basically see an increase in grain size by about 7 nanometers. And there's a strong dominance in 001 texture for both conditions that we're looking at. And it seems that the aging treatment also reduces the large angle grain boundary density by about 0.5 per meter. We then took that same material and look at it from the cross section. Also looking at the growth direction here and see the orientation of grains and grain boundaries. Nothing much outstanding here. And then we performed a TEM EDS mapping in cross section and plan view in order to see if we could pick up any aluminum distribution along grain boundaries or whatsoever. And as expected, there's always a bit of aluminum segregation between the film and the substrate. And after aging, we see a slightly weaker signal of aluminum, hinting at that maybe the aluminum diffused back into the grain boundaries of the film. And for the atom probe analysis, I just want to fly over this real quick. We tried a couple of different things. We tried 3 different temperatures, different laser energies, and we found there's a strong compositional dependence on the laser pulse energy, which was expected. Eventually, we opted for the higher laser pulse energy as we could not reproduce the sweet spot as indicated by the literature to really find a 50-50 concentration between zinc and oxygen. But we faced a low specimen yield at lower laser pulse energies, and hence we opted for the higher laser pulse energies. Various peaks in the mass spectrum, but overall relatively easy to identify, just a few unknowns here and there, just an example. And so let's jump right into the atom probe data. This is a small data set of a as deposited condition. The 2D maps show the aluminum distribution, and it hints a little bit at grain boundaries aligned here, where some high aluminum concentration is found. We place then a cylinder and measure the concentration across these grain boundaries. And there is some variation, but it's not really strong. Overall, we also did high resolution TM analysis and looked at the grain boundaries and kind of see a similar picture. There's some aluminum segregated along the grain boundaries, but very difficult to pick up in this condition. So the overall amount of segregation is relatively weak. We then took the age condition, where now we can see in the 2D map, there's a much stronger segregation of aluminum. It goes up to 9% of aluminum. Also in the atom map, we can see that there's a much stronger structure of the nanocrystalline grain boundaries visible based on aluminum segregation and formation of aluminum oxygen complexes. Again, we took a linear profile just to look across this whole region of grain and grain boundaries, and we can see that now there's actually at the grain boundaries a very, very strong segregation of aluminum, as was to be expected after this aging treatment. And we then performed a 2D concentration map analysis, looking at a bit of a smaller scale here, and what we can see is along this grain boundary, it's actually little islands or little clusters that are relatively rich in aluminum. And if we then go ahead and cut this region out and compare it to high resolution TM, images, we can also see that in the TEM, we actually see bright spots as aluminum segregation along the grain boundary. And we find the same in the atom probe data, matching that really well. Little clusters of aluminum atoms, just maybe 10 atoms or something like that, really small clusters. Triple junctions have quite some aluminum, and the grain boundaries in general. And now we are seeing up to 6% of aluminum at grain boundaries. So now we were wondering, can we quantify this a little bit more? And we decided we want to try interfacial access mapping, but had to get more grain boundaries into our atom probe data set. So we did a cross-section lift out, rotated the thin film, which was only 100 nanometers in thickness. Then we had samples that contained a whole lot of grain boundaries. So this shows just a small subset of this data set where we performed interfacial access mapping, and now can really nicely see how is the aluminum distributed along the grain boundaries. So we picked two different locations, one that had more and one that had less segregation of aluminum, and we find that the areas that are actually showing more aluminum contain up to 2.5 atoms of aluminum per square nanometer, and we think this might be precursor to aluminum precipitates later on. So we now were wondering if we can quantify this a bit more and identify where aluminum is clustering. So we're trying cluster analysis, which ended up being quite frustrating. And the search of Dmax, of a proper Dmax value was quite a challenge, because it seemed like it could be any value. And we then tried something different. We tried to outsource the choice of Dmax and utilize a density spectrum-based analysis. So we then figured out the Dmax value based on that, and then use that Dmax value for the cluster size distribution analysis and cluster analysis eventually. And this is basically how it worked. This is a procedure that was modified by my dear colleague Nikolai Lazarev, using atom probe data in an external program, analyzing it for certain distributions, and then we're also trying to be prepared. What are we expecting to find? So what are the distances that we could possibly observe in between aluminum atoms? So we took all the possible structures in the aluminum oxide, zinc-based phases, and figuring out using Crystal Maker what are the possible distances that could be there between aluminum atoms, so we could identify in which phase or where the aluminum is actually sitting. And this is how such a distance spectrum analysis looks like, so basically a converted density spectrum. And now we were correlating the aluminum from different phases to the peaks that we observe in that spectrum, and we can see that there's quite some strong evidence for aluminum clustering here, and then also aluminum oxide clustering, and perhaps some presence of aluminum in other phases as well. We then went ahead and used that for cluster analysis, and now what we see is that using these Dmax values, we actually get clusters at different locations in the material. So the aluminum peak seems to correspond to small aluminum clusters within the grains. As we take it further to the next peak, clusters appear at the grain boundaries, but also within the grain still. And then peaks 3 and 4, yeah, this is a little bit difficult at the edge of the data set. It could be that that might just be an artifact. So we then did the same thing for the aged condition. Even stronger peak, showing now the two different positions that we could possibly observe for aluminum, and still a very strong peak here for all these different phases where aluminum could be. Same thing again, we performed a cluster analysis using these 4 different Dmax values, and we can trace that there's clustering within the grains, appears small clustering along the grains, and as we move to higher Dmax values, we also move out to the grain boundaries and now really larger clusters that we can now connect to those phases. So here we are seeing pure aluminum clusters possibly, And for peak 4, we see that it might actually more likely be aluminum oxide clustering at the triple junctions at the grain boundaries. One thing that needs to be pointed out, though, is by working with different Dmax values, it can very well be that a larger Dmax value would also cover clusters from smaller Dmax values. So that's something that needs to be considered. Overall, this study is still work in progress, and at a lot of places we ended up having actually more questions than answers, also about the fidelity of atom probe data and where's the limit and where we can make interpretations of what's going on. Generally, I think it's a great tool to figure out potential to optimize processing routines for such materials. And we see segregation along grain boundaries and triple junctions. Cluster search is a very powerful tool to really understand the locations and role of dopant atoms. Yeah, I'd be curious to explore that more, and also very interested in further quantifying this cluster analysis on this material and these different types of clusters that we found. And artifacts obviously need to be considered, especially at such a small scale. With that, I would like to thank you for your attention, and also say a special thanks to Nelly van Derke, who was my PhD supervisor about 12 years ago and introduced me to atom probe tomography and this wonderful community. Thank you very much.
Okay, thank you very much, Florian, for a really interesting talk there. So we probably have time for one question if anyone would like to pose a question for Florian.
There is one in the chat, David.
Thank you. So Ross is asked, you can see the chat?
Yeah, I can see it. How do I account for detector efficiency? Oh, that's a good one. So as we used to leave 5000, the detection efficiency was pretty high, and beyond the capabilities of performing the cluster analysis within the IVUS or AP platform, we didn't further consider the possible impact of detection efficiency. But that's a good point for looking at such small clusters. That certainly may be an impact. But I also was not too concerned about it, as I thought, okay, we are already working with an 80% detection efficiency, which is not too bad. But that's a good point. Probably should look further into that. Thank you very much.
Okay, thank you again, Florian, and thank you to all of the speakers for this session. We're going to close the session this morning, but some really good talks from all, and we'll be reconvening at 9:35 Beijing time. So that's in about 15 minutes. Okay, thanks.
Close your eyes. What do you see? Do you see yourself, the path in front of you, the next step? Do you see your ambition, the cutting-edge approach that opens new dimensions in medicine, the biggest miniaturization that lays the foundation for the digital revolution, the holistic perspective that transforms humanity for good, the progressive vision that changes everything, the way you see the world, the way you capture moments, the way you transcend knowledge, the way you define precision and productivity, the way you live, move, love, heal, think, are. Open your eyes. Can you see it? Together, we are challenging the limits of imagination. For those who see beyond. Zeiss. Seeing beyond.
In today's challenging environment, scientists and engineers need to accelerate discovery processes. CAMICA offers unique, high-performance analytical instruments to help them unveil the secrets of life and materials at the micro, nano, and even the atomic scale. Founded near Paris in 1929, CAMICA rapidly established its name by pioneering first electron probe microanalysis, followed by secondary ion mass spectrometry, and more recently, atom probe tomography. Ever since, we've maintained our R&D investments at their highest level and partnered with leading academic institutions in order to explore new techniques and technologies. Today, CAMICA is part of the Materials Analysis Division of AMETEK, a global manufacturer of electronic instruments and electromechanical products. We have locations all around the world and strive to expand our reach to new geographical frontiers in order to foster emerging scientific players. Our state-of-the-art production facilities in France and the US allow our experts to develop the most sophisticated microanalytical tools used for research and process control applications in materials, semiconductors, geology, environmental and life sciences. Huge investments are made worldwide towards the development of stronger, lighter and more durable materials for transportation, energy production, aerospace and defense, and consumer products. Materials scientists rely on CAMICA instruments not only to gain a deeper understanding of the properties of materials, but also to predict their performance in real world. CAMICA also accompanies semiconductor manufacturers as they explore the boundaries of physics. Our metrology tools enable the production of latest generation electronic devices, contributing to a world where communication is faster and more reliable. From understanding the microstructures of rocks and the genesis of the solar system to revealing water and soil pollution processes, CAMICA provides the tools for writing the history of the universe and creating a safer environment. Offering novel and powerful instruments for studying intra- and transcellular metabolic pathways, DNA expression, virus penetration, and drug localization, CAMICA enables important medical advancements. Thanks to such a wide spectrum of applications, our instruments have been adopted by top-ranking academic and research institutions, as well as major industrial corporations all over the world. Their satisfaction and success are our main focus. The expertise and passion of our teams will enable us to further push the limits of microanalytical instrumentation and help our customers reach the highest performance in their specialized fields. CAMICA, Science and Metrology Solutions.
Atom probe tomography. It's the only material analysis technique that offers both 3D imaging and composition measurements at the atomic scale. And it's contributed to significant advances in science. Here's how it works. The solid material being studied is prepared in the shape of a needle, with an end radius between 50 and 100 nanometers. That's 10,000 times smaller than the width of a human hair. The needle is frozen at a temperature colder than the dark side of the moon to hold the atoms in place, and is biased at high voltage, between 1 to 15 kilovolts. As a result, the sharpness of the tip and the high voltage induce an electrostatic field at tens of volts per nanometer, right at the tip's surface. Then, through laser or high voltage pulsing, one atom at a time is removed from the surface by field evaporation and projected onto a position-sensitive time-of-flight detector. Here's what that does. It allows you to simultaneously measure 1. The XYZ positions of the ion impact, and 2. The atom's time of flight, which can identify the element. Together, these pieces allow you to create a 3D reconstruction of your sample with up to 80% detection efficiency. Put plainly, APT gathers valuable data that's otherwise hard to obtain, providing information that other methods can't. Information, for example, that enabled higher efficiency LED light bulbs, significantly reducing electrical consumption worldwide. CAMECA is the exclusive manufacturer of atom probe tomography technology. Our LEAP and ICOS instruments are at the forefront of material science research. Want to learn more? Download our atom probe tomography tutorial, a practical introduction to the APT technique, or have a look at the 2018 Materials Research Society webinar, An Introduction to Atom Probe Tomography and Its Applications.
Can you see that data?
That looks like Adam is, Dave.
Hello, everyone. My name is Dieter Isheim, and I'm going to be the chair for our next session, the 8th technical session, which will include talks about geological and biological materials, as well as functional materials. At the beginning of our session, I have the pleasure to introduce our next invited speaker, Stephen Reddy. I think he is ready. Stephen Reddy is a professor at Curtin University And at Curtin University, he directs and founded the Geoscience Atom Probe Facility. He had a award in 2013, that's almost 10 years ago, to set up the first dedicated atom probe facility to geomaterials. His research is focused on the development and application of APT to geoscience problems. Beyond that, Steve has a lot of interest in fundamental relationships between mineral defects, interfaces, and elemental transports in minerals, specifically in relation to geochronology and economic geology. Stephen has a pretty broad research background. I was impressed to learn ranging from continental scale tectonics to microstructural and geochemical processes. So that's basically atomic scale to Earth scale. That's quite a few orders of magnitude length scale. Stephen has a special interest in developing high spatial resolution microscopy techniques. Today he is presenting at our conference a talk with the title Atom Probe Characterization of Mineral Interfaces. Steve, are you ready to speak?
I am. Can you see the slide?
We cannot hear you. Perhaps you are muted.
No, I am not muted. Can you hear me?
Yeah, I can hear you, Steve.
Yeah, same
Yes,
here.
I can hear.
We still have no audio. Oh,
I think everyone
No, it's
else.
okay.
Okay. I'm sorry. So,
But you can see the slides?
we can see the slides and we can hear you.
Perfect. Okay, well, thank you. Thank you to the organizers for inviting me today to give you this sort of talk on mineral interfaces. What I want to try and do is give you an overview of some of the issues that we face as geologists working on these sorts of problems. But I'm cognizant of the audience I have, and so what I want to try and do is try and address some issues that have been sort of topical throughout the conference so far. So I'm going to try and say something a little bit about hydrogen in interfaces and something about carbon, and I'll also try and touch on the longevity of and stability of interfaces in the geological record. And some of the examples I'll use are also sort of functional. Well, they're minerals that are also functional materials. And so hopefully that gives a bit more interest to some of the things I'll talk about. So my computer's gone dead. All right, so I thought I'd start off with this slide. So this is a slide I created for a geological audience, but you will probably gather that a lot of the features that we're seeing here are common to the material sciences world, and really the interfaces in crystalline materials are very similar from whether it's a manufactured material or whether it's a natural geologic material. So the main things that we're sort of dealing with, I guess, are things like here are some different phases in green and yellow with different orientations shown in yellow, and we're dealing with sort of phase boundaries, grain boundaries of which there may be high angle boundaries or low angle boundaries, and then things like twin boundaries. And so there are a lot of similarities between what we might be interested in from a materials point of view and what we might be interested in from a geological point of view. The issue with the geological point of view, well, in the materials world, we have a very, we tend to use a limited amount of components, and we have well-characterized thermal histories for the experiments that we are running. Whereas in the geological world, we have far more complexity. So we have more complexity in terms of the number of components from the chemical point of view. We also have a much longer and less well-constrained history. both in terms of temperature and in terms of other sorts of processes or features such as fluid interactions and pressure evolution. And so the thing that we are kind of dealing with is the issues that we're dealing with are kind of shown in this slide here. This is EBSD data from a rock that is dominated by a mineral called olivine, which is or a forsterite, which is an important mineral in the geosciences because it forms a lot of the mantle upon which the crust basically moves. So it's responsible, the deformation and the evolution of this material is responsible for controlling sort of plate tectonics on a large scale. And we can see in here that we've got these grains that are reasonably large, but we have a series of recrystallized domains. We have domains where we have fractures. We have a number of different types of phases. And so the question is what sort of interfaces will be important within that context, and how do we go about assessing those? Now we know that from experiments that interfaces are critical within geological context. So here we just have three examples of how interfaces have been shown to be important. So if we think about deformation, we know that probably in this asthenospheric mantle, the bit that is flowing and allowing the crust to move, that the main deformation mechanism is likely to be dislocation accommodated grain boundary sliding. So the grain boundaries there are critical. We know that when it comes to diffusion, that diffusion along interfaces is much faster than diffusion through the mineral lattice. And so diffusion, the presence of interfaces and the scaling of those interfaces affects diffusion within our system. And we also know that properties that are critical to understanding some of the Earth's structure, for example, electrical conductivity here. When we look at olivine crystals, we find that they have conductivities that are very different from when we deform those and we introduce interfaces. So from a geological point of view, we know that interfaces are important, but we know very little about them. In contrast, I suppose, to the materials world, where there's a large amount of data about the evolution and the processes that take place within interfaces. So here's just one example that I quite like that shows carbon in steel. And around all of that work, there is a framework of things like complexions and complexion transitions that is really quite sophisticated when we think about interfaces and we compare that to what we know about interfaces in geologic materials. So in geologic materials, there's not been a lot of work done on interfaces. There's some pretty outstanding work back in the early 2000s that looked at TEM-based EDS analysis across interfaces, and we can see that there are some hints of segregation. And when we look at things like peak to background counts across those sorts of interfaces, again, these are in olivines, so this important mantle material, we can see that there's some evidence for segregation. But until the development of the atom probe and the application of the atom probe to mineral interfaces, there was a very limited amount of knowledge about the types of segregations. And even though there's a little bit of work here which is dealing with olivine, that there's hardly any data at all on all of the other minerals that are existent in the planet. So we're coming from a background where we're trying to catch up, and and it's not always easy. All right, so what I want to do is give you, I want to basically go through some of the data that we have collected and published around the different types of interfaces that we might see in minerals. And what I want to try and do is give you some examples, but then show you some potential applications for why this kind of research might be important. So I'm going to start off on phase boundaries. And here are two examples. So this is an iron meteorite. This is a lead telluride grain that's sitting within a troilite, which is an iron sulfide. This is about 4.6 billion years old, this interface. So it's an extreme example of aging, I guess. The altite here, lead telluride, is interesting because it's interesting from a geologic point of view, but it's also a thermoelectric material, and that thermoelectric material has been, if you dope that with silver, then you can optimize those thermoelectric properties. And so there's a bit of work in the material science around the use of lead telluride and doping with silver, and we can see natural examples of that in the geologic world that perhaps researchers are not aware of. On the right here, we have some of the important phases that might be important from a sort of a minerals, so from a critical minerals kind of point of view. So indium, for example, is largely found in zinc sulfide deposits, a mineral called sphalerite. The assumption when we try and extract that indium from these materials is that that indium is homogeneously distributed within that sphalerite phase. And here's some data from sphalerite, which basically shows that we have segregation of chalcopyrite, which is a copper iron sulfide, into these lamellae. And then situated on the boundaries of those lamellae is where the indium segregates to. So here we have, no longer is the assumption of chemical homogeneity in these things is valid. We can see that the indium, the material that we might be interested in trying to extract from these minerals, is spatially located on interfaces. And that may, if we can optimize the extraction of that indium, then economically and maybe environmentally, that we have a lot less impact on the extraction technologies that we need to pull that material out. And of course, that sort of material, indium, is important in terms of the energy transitions and all that sort of stuff, the materials that we need to switch from a hydrocarbon-based energy system to something that's more modern. So there's some examples. Here's another example, just to show, again, some complexity. So here we have a rutile grain, which is a titanium dioxide. And within that, we can see that we have these little inclusions of a material called monazite. Monazite's important from a geologic point of view because it's used for dating. It incorporates uranium and thorium in its structure, and that can decay to lead. And that lead we can use to date materials. And so we were interested in trying to date these small inclusions. And what we found was at the interface of the rutile and the monazite, we have some segregation. So a lot of our lead is segregated in here, and so are some other trace elements. But we can also see that we develop these clusters, and these clusters seem to be different for different types of elements. So it's not a simple precipitation kind of process where everything is the same composition, but we get these different segregations that is quite uncommon. But if we can try and understand this sort of process, then it might help us to perhaps manufacture materials in a way to produce more complicated manufactured materials, I guess. All right, so we know that things segregate to boundaries. So can we use that as some sort of application? Well, what we try to do, we've worked with a guy called Grant Douglas at the CSIRO, the Australian Government Research Centre. And what we've done is we've gone to a uranium mine where we have uranium and various actinides that are sitting in fluids, in water that's at the Earth's surface as a contaminant. And we've tried to think of ways that we can extract that material. Now, one way we can do that is we can basically add another fluid to that contaminated water to grow hydrotalcites. They are clays and they strip out the uranium and all the actinides, but they are not very stable from a geologic point of view. So we need to do something else. So what we've done is some heating experiments to try and look at what happens when we heat those hydrotalcites that have been used to extract all of those radionuclides. And we've targeted some of the boundaries. And when we look at those boundaries, what we see is that the uranium and the nasty actinides, etc., are segregated to the grain boundaries. And here you can see the sort of the compositional profile across that boundary. We can see that a lot of the uranium there and the calcium and the rare earths that we might be interested in trying to isolate are now captured those grain boundaries. So there's a useful, potentially a useful approach in terms of developing repositories for noxious materials. Okay, so let's go to grain boundaries and say something about typical grain boundaries. So this is there are a range of different types of grain boundaries, so boundaries within grains of the same composition. And this is an example that I want to show you just because of, well, there's a couple of things. First of all, we thought that this would be quite a simple system. This is a copper-3 platinum alloy found in oceanic crust. So the only thing that's happened to this rock is that it formed as the oceanic crust during some sort of plate drifting kind of thing scenario. And then it's been altered by seawater. And we're interested in looking at, we've got a project that's interested in looking at the platinum group elements and how they move and where they are located within these systems. Now, the amount of platinum group elements in these rocks is very low. It's at a few parts per billion. And so we're basically trying to develop strategies for looking at these alloys that capture these rare earth elements. And you can see that this natural phase timanite, which is a copper-3 platinum, is really quite complicated. You can see here I've drawn in some isoconcentration surfaces that represent the iron and platinum, although the bulk composition is largely Cu3 PT. There are all sorts of segregations, and the animation for this is quite nice. So what I'm going to do is show you an animation that basically slices through that atom probe needle, looking at how what the structure looks like in 3 dimensions. And so here is that phase. We can see the copper-3 platinum is the bulk phase, but we have these grain boundaries that are enriched in cadmium, and along those grain boundaries we're also seeing the segregation of iron, locally sulfur, and things like rhodium that are really kind of taking advantage of these interfaces. And the issue here is that we thought that this would be a homogeneous material with very little variation, and I think that this represents, when we look at copper-3 platinum, when you cool it down below about 800 Kelvin, there are some transitions in there and the development of antiphase boundaries. And these are natural examples of those sorts of processes that people have explained or described from the materials literature. Now, I think in this particular case, there's, as far as I can find, there's no work at all on the segregation of cadmium to copper-3 platinum boundaries and how that might affect the properties of that material. So by looking at these natural examples, we can actually say something useful, perhaps something that might contribute to the materials world and the manufacturing of new materials. Okay, so let's move on to the next example. So what we try to do is do a systematic approach to understand how these boundaries, how we can look at these boundaries. So in this particular case, what we've done, and this is work of Rick Verburn in his PhD, is we tried to look at twin boundaries. So situations where dislocations are not migrating, so we're not capturing trace elements into these dislocations by a mobility process. It's to do with diffusion of material into those dislocations, and we're trying to understand whether the dislocations are acting as fast diffusion pathways or trace element traps. And this is quite a nice example. Again, it's rutile. We've looked at this interface in here. We can show, based on the spacings of these dislocations that we can see in the TEM and what we see in the atom probe, that these linear features and these complications that we see in here are related to the dislocation structures that we see in the TEM. And when we look at the compositions of these interfaces and these dislocations in particular, what we find is that there's a whole range of different types of segregation and different amounts of segregation of material within those dislocations. And that doesn't reflect the diffusivity of those materials. We can see no relationship between diffusivity in the host and the degree of segregation. And it seems to be very much dependent upon the individual element that we're interested in and the mineral that those dislocations are developed in. In this particular case, zirconium is important because it's used as a geothermometer. The amount of zirconium is used to tell us something about the temperatures of these minerals and when they form. And by trapping or releasing this zirconium at various times, it messes up that that particular kind of geothermometer, which has some geological implications. But typically what we do is we target boundaries that we identify in things like EBSD data. So here is a pyrite grain. Here is a particular boundary that we are interested in. And when we look at that boundary, what we find is segregation to those dislocations. And in this particular case, it's important because here we're finding that the gold in these samples is segregated to dislocations. And again, that has importance for how we might think about extracting gold from these minerals in which the gold is hosted. Okay, so one of the things that would be, because of the complexity that we have with interfaces within geologic materials, what we've tried to do is come up with a system by which we can systematically analyze boundary types. And so what we've done is basically looked at grain boundary character, and we're going to go through a whole series of experiments that look at how those different parameters change the degree of segregation, basically in different types of boundary types or interface types. And this is the first of those studies. It's the only one we've actually got around to publishing yet. But this is basically just looking at similar slip systems, but different amounts of misorientation. And what we, and again, this is in olivine, and what we might, we didn't find anything that's not too expected. With increasing amounts of misorientation angle or disorientation angle, what we find is that the segregation is increased. So we find greater concentrations at higher grain boundary misorientations. So nothing that you wouldn't really expect, but it's nice just to show that. Now, one of the things there that's quite interesting is that if we look at this this data in here for the OH peak, so this is at 17 Daltons, what we find is that there's a concentration here along the interface, and that's associated with all these other trace elements, but the only one that's not really present in the olivine in the host mineral is chlorine. And we know from the geologic context of these samples that the deformation in these samples was taking place in fluid present conditions. And so it's tempting to say that the OH here is actually a reflection of the real distribution of hydrogen within our samples. Now that's important because hydrogen, just as it does in the materials world, it is responsible for causing weakness in geologic materials, and the presence of hydrogen can fundamentally affect the strength of rocks. And so understanding whether this is real in terms of real hydrogen or water along those interfaces, or whether it's something to do with the interaction or the field interaction with that surface, and we're looking at contamination from the chamber, is something that's quite important for us. Now, there's quite a bit of work recently that's tried to look at this within geologic systems. There's a group at APT&M have done a similar approach, and the conclusions seem to be that the 17 and 18 peaks in geologic materials seem to correspond to the presence of water that is structurally bound in the lattice of the materials that we're looking at. And I think one of the examples of that best shows that is this little experiment here that we carried out. It was published last year. So these are samples, again, olivine samples. These were collected by the Japanese Space Agency during their Hayabusa mission to asteroid Itokawa. So these are basically bits of olivine fragments that have been sitting on the surface of an asteroid that have been collected from space, brought back, and then we've analyzed the surface. And the reason we're interested in analyzing the surface here is that there is an idea that the implantation of hydrogen associated with the solar wind should produce a layer of hydrogen on the outermost parts of these minerals. And that's an important component because if you look at the water composition of meteorites, they don't have the same composition as Earth. We need a solar composition to be added to those meteorites to produce the bulk Earth hydrogen isotopic composition. So we're looking for a missing solar component. And when we look at these grains with the atom probe, what we see is that there seems to be a profile here that's easily, most easily seen in the OH. And so if this is a contamination feature, then we have some issues. It's not real. So we've done some experiments using deuterium and using deuterium radiation of samples of olivine, and looked at those. And what we find when we look at the proxygrams is that, or look at the depth profile, what we find is that this oxygen hydrogen or oxygen deuterium peak seems to be consistent with what we'd expect if that water or if that deuterium was now structurally incorporated into the mineral rather than being contamination from the chamber. So there, I think we've got some good evidence that the OH and potentially the OH2 peaks are reflecting structurally bound material water in our samples. Okay, so I want to say a quick thing about carbon in low angle boundaries. So the reason carbon might be important is when we look in the Earth's crust, there's a series of electrical conductivity variations that are very difficult to explain when we look at rocks. The material that you would expect to see in rocks to produce high electrical conductivities just don't seem to be there. So there's this missing kind of component of electrical conductivity that we need to try and find. So these here are showing electrical conductivity variations in an area of Central Australia, and we picked one of those to try and have a look at what could be the cause of that electrical conductivity variation. And the material we're going to look at is a monazite, which is a rare earth element phosphate. We've done EBSD on that, and it shows that it's deformed. And we picked one of those boundaries to look at from an atom probe point of view. And when we do that, we get a complicated spectra. And I don't want to go into too much detail with the spectra, except that I want to show you this. I want to do a close-up of this ranging at around 44 to 44.5 Daltons. Okay. So in this particular case, when we look at the 44 peak, what we see is that there's some spatial heterogeneity in here that defines these interfaces. When we look at the mass, when we look at the yttrium peak, and I can't see that, but it's under here somewhere. When we look at the yttrium peak, we know that that's really nailed on in terms of the mass calibration. And when we look at the potential peaks that are looking at around 44, then the strontium and the FeO2 peaks don't really match. Neither does the SiO, but the CO2 does look as though it's a reasonable match. And if we go down to the 28 peak, which would be potentially CO or Si+, what we see is it really is quite fixed on the CO+ peak. And then when we go down to 14, which is the silicon, and the 14.5 here, which is the silicon minor isotope, what we see is that we lose the spatial variation that we're seeing, but these seem to be consistent with the silicon peak. Based on all of that, what we would argue is that these interfaces here that we're seeing are enriched in carbon. And so there's potential that there is a carbon phase along these boundaries. And if we take a look at those in terms of the atom probe reconstructions of the data, what we see is that those low angle boundaries seem to be the places where that carbon 44 peak is enriched. And we can see here that it defines the planar features, the low angle boundaries, but on those planar features are a series of dislocations. And those features are a 3D network throughout that deformed grain. And I would argue probably extend into the grain boundary network outside of this particular grain. Now,
we have 5 minutes left, Steve.
Great, thank you. And so here we have this carbon segregation. The conditions that these rocks are formed and have been deformed, we're looking at a graphite stability field. So these are graphite films along low angle boundaries that can explain the conductivity variations that we see in the Earth's crust. Okay, the last little bit is how long do these interfacial variations in composition vary? The best example of that, and the only example I am aware of, is it comes from pyrites from the Watersrand gold deposit, where we've looked at the interfaces and to try and understand some of the complexities within this. So these are deformed grains. They've got a complex deformation history that involves plastic deformation, some brittle deformation. And here we have a series of, my animations aren't working, but here we have 2 different sites within our sample. And within those sites, we have these 2 different lead distributions. And when we look at the lead distributions in terms of the whole basin, we find that there's mixing between 3 billion-year-old lead and 2 billion-year-old lead. And what we're finding in the low angle boundaries is that the lead that we're seeing is this component that is has an age. The isotopic composition places that capture of that material from those boundaries into at an age of 2 billion years. So the evidence here is that these boundaries have lasted for 2 billion years, and they haven't been modified, and the lead composition hasn't changed since that time. So once these things form in geologic systems, they seem to be quite durable. They seem to last a long time, and so that gives us some constraints on aging, I guess, is how long these have been developed for. All right, so that's kind of an overview of some of the things that we've been working on. It seems that trace element segregation to interfaces in geologic materials is ubiquitous. We can use atom probe to obviously quantify those compositions, both from an elemental point of view and an isotopic point of view. That can tell us quite a bit about that can tell us quite a bit about geological. It has quite important aspects from a geological point of view. But I think the natural examples can provide some constraints or some insights into the complexities that you can potentially develop that may sort of spill over into the development of new materials and the material science kind of field. All right, so I will leave it there. Thank you very much.
Well, thank you, Stephen, for this very informative presentation. Really interesting, the variety of minerals and deformation structures. And I would think, if nothing else, a big overlap between geosciences and material sciences is that the presence of defects, wherever there is a defect, there's action. If nothing else, yeah. that was very interesting. We have time for a couple of questions. I'm checking the chat. If there's anything in the chat, if you have a question, you can raise your hand. You can simply unmute and speak up. While we are waiting for more questions, Stephen, I had one question. A couple of slides back when you mentioned, let me start from this side. I found it quite interesting, the deconvolution of the peak at 44 Dalton, CO2 yes. versus SiO versus strontium 88 2+. I was wondering, you were switching forth and back a little bit between carbon segregation, graphite film, and CO2. From physical metallurgy, we work a lot with carbon in the context of steels. And in the atom probe, usually we can distinguish carbon as an elemental species, with peaks, of course, at 12 and 6 for 2+. I was wondering about if you see a peak at 44, you have a reason to ascribe it to CO2. What's the connection? Why do you think it is carbon, or why did you say it was carbon if you detected it as CO2?
So I think what we find when we're analyzing geologic materials is that we often get the molecular species, and there's a combination with oxygen, because oxygen is ubiquitous in most of the materials that we're looking at. So so the reason the main peak that it could be from that it is really either the SIO peak. The others I think we can rule out because they you wouldn't expect those elements in that monazite material anyway. We do sometimes find trace silicon, but the issue is that when we look at the real silicon peaks at 14 and 14.5, the 2+ peaks, we see no spatial variation, and so we don't see the same pattern in the 44 peak. So my inference there is that can't be a silicon related peak, and then so the only thing we've got left is the carbon. Now, the other relationship there, which I didn't show, is that those spatial variations in the atom probe needle that we see at the 44 peak are mimicked by the 23 peak, which is sodium. And so we have an association of sodium with something that looks like carbon. Now, within these rocks that we're looking at, these are really these are dry rocks. Essentially, they've been metamorphosed at about 1,000 Celsius, and there's association there in fluid inclusions of carbon, usually in the form of methane or CO2, with sodium, which is as part of a brine. And my interpretation of how we get the sodium and the carbon into the low angle boundaries is that when we deform that rock, those fluid inclusions break down and give us a source of sodium plus carbon that then infiltrates and gets into those low angle boundaries. So it's it's not exactly nailed on that it's carbon, but I don't think there's I don't think there's any other arguments. You know, when you put it in terms of the context of the rock, the history, and you look at the potential carbon versus silicon distributions, it has to be a carbon peak, and it wouldn't be CO2 in those sorts of conditions.
Thank you. Yeah, I definitely agree. Context is very important, and the thermomechanical history of these rocks is definitely complicated, and but is important for understanding the structure and of course also of what molecular species we have in the mass spectra. Stephen, I wanted to thank you again for a very interesting talk. Unless there is a very urgent question, I wanted to propose to move any further discussion offline. Stephen, nice to meet you virtually.
Yeah, thank you.
And we now move on to the next presentation, which actually I believe is recorded. The speaker, Tommaso Tacchetto, could not be at the conference. And the next presentation has a title, Crystal Plasticity Enhances Trace Element Mobility in Garnet Minerals. So we stick with the geoscience topic about plasticity in garnet. Can we start the presentation, please?
Hello, everyone. My name is Tommaso, and I'm very pleased to be presenting results of my research, and in particular, the investigation that I've been conducting on trace element mobility during crystal plastic deformation of garnet. As you know, rocks are polycrystalline materials in which grains are separated each other by grain boundaries. Grain boundaries are defined as two-dimensional interfaces that mark the change in lattice orientation between adjacent crystals of the same phase. And in particular, I'm going to refer to this variation with the terminology disorientation angle. Although very narrow, restricted to a few nanometers, these regions have been shown to affect a wide range of mechanical and physical properties of rocks during deformation. For instance, they can represent regions of enrichment of particular trace elements. They can control the strength of the aggregate by variation in deformation mechanisms. They can represent fast diffusion pathways for element mobility. For instance, diffusion along grain boundary as order of magnitude faster than volume diffusion through the crystal lattice. And they can represent pathways for percolation of fluids at crystal depth, and therefore the enhancement of metamorphic reaction along the interfaces. Therefore, it is clear that the investigation of interfaces properties is a key point for a better understanding of those that are fundamental rock processes. So in this study, I've been investigating garnet, which is a cubic silicate mineral. Garnet is a common rock-forming mineral that occurs in a variety of mineral assemblages and in geological environments. And in particular, because of its robust chemistry, it is widely used in geology for reconstructing those that are the complex pressure and temperatures evolution path of rocks during geological time, and it has strong geothermal barometrical applications as well as in geochronology, and it can be used to understand composition of primordial melts, and also it can be used to understand those there are properties of rheological properties of the lithosphere. And in particular, the last one, because garnet is a common constituent of groundlites and key constituent of eclogites and mountain peridotites. And these rocks are part of the lowest portion of the continental crust, and therefore understanding those that are the rheological properties of garnet during the formation can give us access to a better understanding of rheological properties of the earth. So far, there have been quite a few studies on garnet rheology, and in particular, this study have shown transition from a brittle regime to a ductile regime at about relatively higher temperatures. And this study has shown by APT&M applications that crystal plasticity occurs by the formation of subgrain boundaries. In particular, here you can see these locations which are aligned along interfaces. And more interestingly, SEM studies have shown that along these subgrain boundaries, there are chemical heterogeneities. However, there is a debate for the mechanism responsible for these composition variation that can be either attributed to segregation of trace elements or diffusion of trace elements. So the aim of this study is to use atom probe tomography to atomically resolve this debate. The rocks that have been used are part of my PhD study from southwestern Norway, from close to the Bergen Arcs. And in particular, these rocks are Grenvillian granulites, which were formed at high temperatures. They were subsequently transformed during the Caledonian orogeny into eclogite, following an event of high-pressure metamorphism, deformation, and fluid infiltration. And in particular, these rocks are characterized by these features, which are pseudotaculite, that represent a brittle failure of the rock, which allowed the fluid to infiltrate the rock and the subsequent transformation into higher pressure counterparts. In thin section, the pseudotaculite appear as a glassy dark vein, which is characterized by an aggregate of finer minerals, and this vein cross-cut the rock foliation, and mineralogically we can see evidence of fluid infiltration for the appearance of hydrated mineral, which requires the presence of a fluid. As well as these fluids must have been carrying elements such as potassium and sodium for their mineralogical properties, which is consistent with subduction fluoridated fluid, which is also consistent with the geological context of these rocks. For atom probe tomography study, I've selected this grain, which, as you can see, is cut across by the full vein. Chemically, the garnet is not homogeneous, but is internally zoned, and in particular, elements such as calcium and iron form an enriched rim all along the rim of the grain, both adjacent to the fault vein and to the matrix of the rock. And there are elements like magnesium is instead depleted. And this suggests that there is a process of chemical recalibration that must have been occurred during the formation and probably after the formation. In order to understand the microstructures and the formation mechanisms of the garnet grain and to select possible atom probe targets, I use ABSD orientation mapping, and the data allow to recognize regions of the grain of enhanced intercrystalline distortions. And within these regions, subgrain boundaries are found, and in particular, selected this low-angle boundary here for atom probe tomography study that has a disorientation angle of 0.7 degrees and is consistent with the activation of a known slip system for crystalloplastic deformation of garnet. And therefore, all of these microstructures are indicative of a component of the formation accommodated by this location creep. So the targeted low-angle boundary at the atom probe presents some interesting features. For instance, the enrichment of trace elements along a planar feature. And if we back correlate the orientation, the EBSD orientation mapping with the orientation of the atom probe tomography specimen, it's possible to infer that this planar feature is actually representing the interface of the boundary. So I performed concentration analysis by using proxygons out of isoconcentration surfaces obtained from OH peak and titanium, which were mostly defined within the interface. And as you can see, not only trace elements are clearly enriched at the interface, but also major elements, major constituents of garnet are depleted, such as aluminum, iron, and silica. And this suggests that the stoichiometry of the garnet is respected, and we're not analyzing an intergranular phase between the two grains. So if we summarize together all the findings, there is clear evidence that the main deformation mechanism of garnet is a brittle deformation. However, we found evidence by EBSD analysis of a smaller component of crystalloplasticity, and in particular, deformation is accommodated by a dislocation creep. And dislocation creep, I remind, involves the migration, accumulation of dislocation to high-density dislocation low-angle boundaries, as you can see here in this representation. And there is evidence both mineralogically and for the geological context of these rocks of a fluid phase that was present during the formation. As you remember from the chemistry, this fluid phase is most related to that of a brine, which is a subduction zone related fluid, which carries elements like sodium, potassium, chlorine, etc. There is evidence from EDS maps that garnet has undergone an event of chemical recalibration. So there are elements moving in and out from the grain. And if we put together all of these observation, this study has strong similarities with another study we performed on rocks coming from a close locality to the one of these garnet. And in particular, we investigated low-angle boundaries in olivine, and we observed that during this location creep, common olivine impurities can be segregated along these interfaces, and other elements can be infiltrated if a fluid is present during the formation. And therefore, putting together all of these observation and the similarities is very strong, and therefore we can interpret that even for garnet, the trace elements that we found originally in garnet are in part derived from a segregation mechanism of common impurities, And on the other side, elements that are more related, more consistent to a fluid phase during the formation, like a subduction-related fluid that we know is present along the pseudotacky line, can be diffused along the low angle. So summarizing and concluding, we now know that trace elements segregates to low angle boundary during crystal plasticity of garnet, but also that low angle boundaries are open to diffusion of elements from the outside. So therefore, atom probe tomography has allowed us to understand that compositional variation in the formed garnet is not only derived by segregation, but can be also derived by diffusion or a combination of both. So this study can have strong implication because trace element segregation affect properties of grain boundaries. For instance, the energy of the interface is dependent by the chemistry of the interface, and as well as the diffusion properties along the interface can vary, but depending by the chemistry of the boundary. And finding that at the nanoscale, trace elements are moving within and outside the garnet grain, this can definitely question the chemical robustness of garnet for its geochronological application. I thank you very much for your attention.
Well, Tommaso is not among us today, so please direct any questions by email or other communication. We are moving on to the next presentation by Professor Gregory Thompson from the University of Alabama. This is also a recorded presentation and has the title Grain Boundary Dependencies in Nanocrystalline Phase Separation. Can we play? Oh yeah, here we go. All right.
Hello. Before I begin my discussion on grain boundary dependencies in nanocrystalline phase separation, I'd like to recognize my co-authors on this paper, Rhett Zhou, my former student who initiated this work and has continued on in collaboration with colleagues at MPIE, Reza Kamakali, who's provided the phase field modeling that I'll share with you shortly, as well as Dirk Rabe, Brad Boyce, and Blythe Clark for technical discussions as well as the specimens used in this program. This work was funded by the U.S. National Science Foundation. I'd like to begin with just a very quick primer about spinel decomposition. What makes spinel decomposition a very interesting phase transformation study is that it's often referred to as a barrierless nucleation process. And this behavior results in uphill diffusion, or like atoms diffusing towards each other, and as a result of the free energy curve of the material as a function of its composition. As shown in the upper left-hand corner is the free energy curve, and where the free energy curve's second derivative is equal to 0 are referred to as spinodal points, and they map out a miscibility gap that is shown in the image below it that you see on a phase diagram. Now, what makes this interesting is being considered barrierless free, defects such as grain boundaries, dislocations, and other things are often neglected. In contrary, heterogeneous nucleation often very much relies on these defects. And so what we'd like to study then is how do such defects, like grain boundaries, manipulate or control spinel decomposition, in particular as nanomaterials are becoming more and more relevant in a variety of different metal alloy systems. Now, one of the things I also want to highlight about spinel decomposition is its characteristic evolution with time. In the early stages of this phase transformation, the compositional amplitude is quite low, but given time over the transformation, that compositional amplitude will increase, i.e. that uphill diffusion that you see. And so this will be a characteristic compositional signal to suggest spinel decomposition. The alloy we were going to use is the platinum gold system. This offers a lot of really good experimental advantages. In particular, they're noble metals, meaning that when we anneal it, the platinum gold won't react with the environment, so we don't really have to worry about oxidation or other issues. So it's a fairly clean system. In addition, of course, platinum gold have a miscibility gap that is shown here in the phase diagram. We've taken this alloy, sputter deposited, so we created a supersaturated solution of platinum being the matrix element and gold being the solute. And when we annealed it at 700 and 1300 Kelvin, we can see that we have minimal grain growth too. And this is an attribute of its being considered a nanocrystalline stabilized system. And what we're going to do is focus primarily on the 700K region because we have the least amount of grain growth and the smallest variation in grain sizes, evident by the error ratio shown here. Now, prior work by Sandia National Lab had already identified that gold varied from grain boundary to grain boundary in a platinum gold system. And this is shown in this TM EDS mapping that they've done. They not only noticed that the gold varied from boundary to boundary, but even within the same boundary region, the same boundary plane, they also noticed some variations in the EDS signal that they picked up. But what we want to do is then understand what is the boundary type and what is, in a quantitative manner, the amount of gold in that boundary. To do that, we've correlated electron diffraction, which is very good at crystallographic information, with the atom probe work, which is very good at the chemical identification. And so by doing what's called precession electron diffraction on our atom probe tip, we're able to map out the grain boundary misorientation from each grain, from grain to grain. And being a nanocrystal material, on the order of 100 nanometers for our grains, and the spatial resolutions take to about 5 nanometers, we'll easily be able to achieve this. Using that information then, what we've done is, I'm showing here, is on anneal at 700 Kelvin at 4 and 24 hours. And what you can see in these maps is the initial onset of gold partitioning to the grain boundary, or segregating the grain boundary, shown here in grain boundaries 2 and 3, and some variation in composition. And then once we anneal to 24 hours, very clear chemical partitioning of the gold in the boundary. And this is highlighted by the interfacial excess of those atoms and the grain boundary misorientation. So we see a range of gold concentrations or interfacial excess as a function of misorientation, as well as within the same boundary itself, a difference in the amount of gold. And that can be understood by looking at the grain boundary plane. Here we see a very high enriched region of gold, and then other areas that are less enriched. And so this explains the variation in gold content even if the angles have the same even if the grain boundary has the same misorientation angle. And of course, if we anneal up to 720 hours, this is an extended period of time, we see even further phase separation of the gold into the boundaries and clear onset of secondary phase formation. Here's a STEM EDS map that shows those gold particles that have formed, and then again gold enriching and phase separating itself within the boundary. And this is, even here we can see a sinusoidal oscillation of the gold along the grain boundary plane in the system, very characteristic of the spinodal compositional profile that I noted in the earlier part of my talk. So now we have this experimental data. We want to understand then what is transpiring and what is going on. To that end, we're going to use a density-based phase field approach. Here we take a free energy functional and we make it as a function of the density. So when the density of a system is not in the grain boundary, it's 1. And of course, when you come to the grain boundary, the system isn't as dense, and so there's some excess free volume, and therefore the density drops down. And so to a first approximation, we can use this as a scalar term to understand how the energy changes as a function of the different types of boundaries in the system. We can express that free energy functional in terms of composition, as shown here, as well as a function of the density. And then if we simply make the density 1, we have a self-consistent result that is in agreement with a regular solid solution mixture shown here. So what we've done is we've then taken our PED data where we know the grain boundary types, and we now through atom probe know the concentration of those boundaries, and simulated what those misorientations are, and then related those misorientations to an approximation of what the density change would be in that boundary. To that end, we've simulated this, as shown in this phase field model, of gold partitioning to the boundaries and then evolving into those boundaries. And so the images to your right here are two-dimensional slices that have occurred in this three-dimensional phase field model, with here these green tubes here representing the partitioning of the gold into the different grains. And as our simulation continues, we can see that these particles are enriching themselves further, evident by the red color, and we can see that they're coarsening, and in some cases, even some of the solute is depleting and then being reprecipitating itself in other grains. So it's kind of, the simulation is basically capturing the physics of what's going on with our experimentally showing that behavior. To that end, let's talk about a few of the sequences that we see. Initially, we see that the gold partitions to the high angle grain boundaries. These are shown here, and we see that it seems to wet those boundaries. And if we look then at the character of those boundaries, these are boundaries that are on the order of 39 degrees misorientation, 46, 36 degrees on this side. So what we realize is that the high angle grain boundaries are the first boundaries in which the gold solute partitions. And when it partitions, it seems to wet the boundary. And then as it continues to evolve with time, we can see that those boundaries are starting to then phase separate and having that classical spinodal decomposition reaction. We also realize about this time, we see the onset of low angle grain boundaries. Here is the 9 and 7 degrees also being enriched, but they almost immediately start to phase separate. So we already see a distinction in the character of the boundary and how the solute partitions and evolves. And the subsequent images of the simulation continue to show that evolution and that enrichment that you saw in that live video, to ultimately until we have that clear second phase formation, which we were able to confirm through our experimental work with that STEM EDS map. So to really provide the most convincing evidence that what we're seeing then is spinodal decomposition in the grain boundaries, this upper series of images represent the composition and the area fraction as a function of the various anneal times of 4, 24, and 720 hours. The black line here represents the overall composition of alloy. And what we And so this helps us provide quantitative information both from our phase field model as well as with our experimental model, with our experimental data, excuse me, that what we are indeed seeing is this behavior. But what is really interesting, though, is that in the phase field model, what we see is that gold first partitions the boundaries, enriches the boundaries, and then undergoes spinodal decomposition, and a low angle boundary basically immediately undergoes a spinodal decomposition reaction. To understand this, we are able to see how the relative chemical potential changes as a function of gold content. And what we realize is that as a boundary becomes a high angle boundary or less dense, it requires more solute in order to reach the critical point where spinodal decomposition will occur. Where a low angle boundary, which is closer to a density of 1, is much closer to the bulk composition where spinodal decomposition occurs. And so from the thermodynamics that underlines the phase field model, we're able to understand then this behavior, that simply a high angle boundary requires more solute to be partitioned to it before it can initiate the spinodal decomposition reaction because of the change in its density as relative to a low angle boundary, which is closer to density 1. Similarly, we also see some other interesting aspects that come out of it. One is that as we have a smaller grain size, as you can see here, we also seem to have a lower grain boundary segregation level available in the system. And what is really interesting then is our grain size decreases, the solute starts to partition to those grain boundaries. And so now we create this competition between partitioning to the boundaries and wanting to undergo spinodal decomposition within the bulk of the alloy. And as the solute then depletes out of the interior of our nanocrystalline grains, the composition within the bulk of the grain now is removed further and further away from being in the spinodal and will not undergo a spinodal decomposition reaction. And this is shown here, that as the solute partitions to the boundaries because of the small grain sizes, the chemistry, the composition of the bulk material now is now sitting outside the spinodal and doesn't undergo spinodal decomposition. So very interesting outcome again for modeling. So in summary, with my time quickly coming to an end, we use cross-correlative atom probe and PED to reveal grain boundary character and solute segregation. We can see that that varies as a function of grain boundary type and concentration. We're able to explain that in terms of the spinel decomposition behavior. And so while defects are normally neglected in spinel decomposition, in a nanocrystallinity where the grain boundaries are prevalent and there's a strong tendency to segregate to them, they can play a dominant role. Phase field modeling has actually given us an understanding of the physics of underlying what's occurring in these type of materials and the role that different boundaries have on controlling that phase separation and that spinel decomposition reaction. And clearly, as we get to a smaller size and a higher fraction grain boundaries, the solute becomes more readily depleted out of the bulk of a grain and therefore removes it from having the right composition to undergo spinel decomposition. And so all those phase transformation reactions then occur within the grain boundary itself. And with that, I thank you so much for your time and appreciate your interest in my talk.
Well, Gregory is not present, so we move on to the next presentation, which will be given by Stan Lambeets of Pacific Northwest Laboratory in the USA. And the title is Nickel Surface Interaction with Carbon Dioxide, Heavy Water D2O and D2 Ingress, a nanoscale study by in situ atom probe tomography. Stan, are you ready to present? No, I'm pretty sure we have a sound problem again. We cannot hear you, Stan. Can anyone hear Stan? Ah, yeah. Now we have sound. There was. Can you say something?
Yes.
Yeah. Yes, we have sound. Very good.
Oh yeah. I hope my internet will not will survive. Okay, so if you hear me, I hope. So thank you everybody for being here. It's always a pleasure to participate to the Atom Probe Tomography and Microscopy Conference every year. And so today, so maybe some of you know that I'm a huge fan of chemistry and atom probe cuisine. But this year I will not talk about the operando, I promise. I keep that for the next year. This year I will just present you a more classic study using the in situ atom probe system to explore nickel interaction with CO2, water, and deuterium, hydrogen. First of all, I had the pleasure to acknowledge and thanks my collaborators from the PNNL, Danny Perea, Harun Devraj, that you all know very well, Mark, Elizabeth, and Karen, and of course the program that actually financed this research, led by Andy and David. So this program is the Tritium Modernization Program. So the context of this study is related to the production of tritium via the tritium producing burnable absorber rods. So the idea of such a technology is to produce tritium from the lithium aluminate pellets. And so once the tritium is produced, let it diffuse towards the zircaloy 4 to be stored. But of course, the zircaloy 4, if it's reactive enough to store and interact with the hydrogen, it also can interact with other contaminants due to the manufacturing process, notably carbon monoxide, CO2, methane, and water. And so even if the nickel is known in chemistry to be transparent to hydrogen, so basically the hydrogen comes in and out very easily, it's not necessarily the case of the contaminants. Nickel is very well known in petroleum industry with the reverse water gas shift chemical reaction that converts CO2 and hydrogen to carbon monoxide and water. And so it's very well known that it produces nickel oxides and also carbon coke deposition, which were actually found on used TP bar pieces. And so the question that they have in this program is that, okay, tritium doesn't interact with nickel, but what about the nickel oxide and the carbon coke? And so our approach is to use, since it's a very precise and very small chemical reaction, fortunately for them, we're going to use the in situ atom probe tomography to study that. So for many of you are already got a talk from PNNL, so this is probably you saw that already. So this is our in situ atom probe system. So it's composed with actually chemical reactors that is directly linked by UHV transfer to a LEAP 4000 system. And so the principle of the in situ atom probe is the following. Our chemical reactor can heat up the specimen up to 400 degrees Celsius, and we can expose our specimen to reactive gases, oxygen, carbon monoxide, CO2, deuterium, up to 1 atmosphere. And the idea is that the general workflow is the following, is that we fabricate the specimen first by the electrochemical process, or FID. Then we clean it. We try to have a clean surface by using the field evaporation in the APT. We transfer it back to the reactor. We perform the chemical reaction that we want, that is it's ordered by the user. And then we transfer the result back to the atom probe for analysis. And so if we think about it, and so if we continue to do that, each cycle can be seen on one snapshot of the overall process. So if we keep, for instance, the same temperature, the same pressure, the same gas, but we change the time of exposure only, we can actually see that, only different snapshots of one very long process over the time. And so this is typically something that we did with cobalt in the past. For instance, here, this is the isosurface of cobalt monoxide. So we expose a pure needle of cobalt to oxygen at 350 degrees Celsius. And you see that I drew the isosurface of carbon monoxide. So after 10 minutes in green, 15 minutes in yellow, and 30 minutes in red. And so we can see the progression of the cobalt transformation to cobalt monoxide. So we did the same basically with nickel. We start with pure nickel. So I colored the nickel in green and the oxides in turquoise. So here's the native run. The nickel is pure. That's a good news. I mean, we use nickel for its corrosive corrosion resistance. So this is a pretty good news that we don't have too much oxidized nickel. And when we expose it to CO2 at 350 degrees Celsius during 1 hour, we don't see that much of a result. But after 2 and 4 hours, we see a bit more of turquoise. So I should choose maybe better colors, but yeah. We have turquoise, we have the formation of nickel oxide after 2 and 4 hours. So it's maybe more obvious when we use actually the 2D concentration maps. So obviously in red, it's more oxidized, in blue, and it's not. You see in the native run, we have a bit of oxygen here, a bit of zone oxidized. We clean it after 1 hour of CO2, almost nothing, but then after 2 and 4 hours, we have a very beautiful layer of nickel oxide. And so also what is important, as I mentioned before, is also the question of formation of carbon. We see a bit of carbon, but again, it's known that the carbon stays on the surface, and the surface is a very small volume of the overall results in the APT reconstruction. So it's not such a surprise that we don't detect so much of it. We're going to use another technique, the field ion microscopy, to study it better. But here we go. Here is something that we actually expect if you do a bit of chemistry. Indeed, the CO2 actually oxidizes the nickel very well. And so we try to maybe image, what's going on. So the hypothesis here is indeed the CO2 dissociate, maybe prevent the carbon monoxide reduction. And so maybe that's why we don't see much more of carbon. So as I say, we actually use also the field ion microscopy. And what is interesting in field ion microscopy is that it helps us also to map the surface of nickel. So nickel is a FCC cubic, so face-centered cubic crystal. And so what we can see here, so this is the FIM of one specimen of nickel. And then we do the oxidation after 4 hours again, and we map the concentration of oxygen detected. And we see that like the rhodium, like the platinum, like many other metals, actually the oxidation of those metals are not homogeneous over the entire crystal. Actually, there is more concentration of oxygen in some specific facets. and not so much on the 012. For instance, if we take the iso surface, we see indeed like a flow of oxygen that seems to avoid the 012, but actually oxidize better the 111, the 011, and the 113. So it's even more like this. So we have this little tip that corresponds to a 012 direction of the nickel. So how to explain that? So this is something that, again, we saw it's very similar to platinum and the rhodium, which are also the metals with similar properties. And the idea is that nickel, so nickel 111, 113, and 011 have enough space to interact with the oxygen. It's more a question about what about the 012? 012 is a very reactive facet, and so it's kind of a misleading to think that, okay, there is not a lot of oxygen, so it doesn't oxidize. It's actually a bit the opposite. The 012 is actually particularly sensitive and unstable, and so there is a very quick oxidation and reconstruction of the 012 that result in a passivation. And so we saw that also in the rhodium and platinum, that actually the 012 is a chemical reactor. So it makes a lot of CO2 dissociation, but it doesn't let the oxygen enter inside of the metallic crystal. So we feel that this chemical surface, the surface chemistry is very sensitive to the surface structures. So we saw that it's very sensitive already on the single crystal. It's obviously even more sensitive when you have more damages, like, so for instance, here, those more grain boundaries, or I don't like so much, but like linear defects that we can see here. So, and this zone is actually a polycrystalline nickel, or this one with a single crystal of nickel with a small, actually a small not grain boundary, but a linear defect line. And when we do the oxidation of those different type of specimen, we see indeed that a lot of oxidation in this polycrystalline nickel, and also here the single crystal that is maybe more resistant to the oxidation, while that the presence of this linear defect actually helped the formation of oxygen nickel oxide. Also here with the 2D concentration maps of those two specimens. So now, so the idea here again, so does the nickel react with CO2? Yes, and this is something that we expect. CO2 oxidize nickel very well, more than oxygen or water. We will see that later. So the answer is yes. Now the question is, okay, so if it happens in our TP bar, let's say that we have a bit of nickel oxidation, what's going to happen for the tritium? Of course, we use the deuterium as a surrogate, because we're not rich enough to have the tritium. So we do first the oxidation of the nickel to have this beautiful and thick layer of nickel oxide. And then we expose it to hydrogen, 10 millibars, 350 degrees Celsius still for 12 hours. And here is the result of it. We see that when we expose to CO2, basically what you have is on the top, you have an oxide, and on the bottom, you have the pure nickel. When we expose this, this result to hydrogen, it's reversed. You have on the top the pure nickel, and on the bottom, you have the presence of more oxygen. And when we actually try to see where is the deuterium, it's also where is the oxygen, for the simple reason that most of the deuterium is detected as a form of hydroxyl. So, of course, the oxygen and deuterium actually correlate here. And so this observation can be easily interpreted in terms of chemistry. First, when we do the CO2 exposure again, we have the dissociative adsorption that produce one oxygen and one carbon monoxide. We don't have so much of carbon, so our assumption is that the second dissociation, so the carbon monoxide dissociation, takes too much energy, and actually there is more chances for carbon monoxide to desorb from the surface and leave the oxygen behind. So we start to oxidize the nickel, so resulting into this oxygen diffusion front.
We have 3 minutes left.
Oh, already. So, okay. So when we expose then hydrogen, is the reverse. We actually reduce the nickel oxide to produce hydroxide and water. And so we start to clean and have these final results. But of course, it's not really representative of the reality, right? Because you have oxygen, you have CO2, everything in the same time. So when you expose the CO2 and the hydrogen in the same time, you have actually no oxide, you have a pretty clean nickel. But it's a fake idea to think that nothing happened, because of course, when you have a constant dissociation of the CO2 and the formation of water, you actually enhance the production of carbon. So when I do the FIM, here the FIM of nickel, and I expose it to a mixture of CO2 and hydrogen, what we see here is actually the formation of a dark region that actually are the result of the formation of carbon coke on the surface that block the neon ionization. And so indeed, when you do that for 28 hours, you see the formation of carbon on the surface. So you need something that is more surface sensitive, like the FIM, to image the formation of carbon. And you need a lot of energy, like a high energy laser field evaporation, to remove this carbon, and still on the 011, the carbon stays there. So here again, the mechanism is pretty straightforward. We are actually a continuous reduction of CO2 that produce this carbon on the nickel surface. So then I will finish with what is the effect of the water. So when we try to oxidize the nickel with water, it doesn't work, not like the CO2 when we do the straight comparison. So here on this chart, I see that I detect more atoms of oxygen when we expose to CO2 than actually the water. So behind this is that there is this idea that the dissociation of CO2 on the nickel is requires less energy than actually the water itself. But it's very important to remember that the adsorption of CO2, though, it takes more energy than the water. So actually, there is a competition between the water and the CO2 to oxidize or react with the nickel. And this is more obvious when we mix the CO2 and the water together. We see that the oxidation is actually collapsing. The idea is that because the water already has this constant dipolar moment, it's easily absorbed on the surface of the nickel, but does not dissociate, while the CO2 is actually just a question of chances that actually it absorbs and dissociate on the nickel. So there is this idea that actually, of course, when we add the hydrogen, is even better. I mean, the nickel doesn't oxidize at all. And so here there is this idea that actually water prevents nickel oxidation and probably also increase the formation of carbon. So in conclusion, so thanks to the in situ atom probe tomography, we saw the CO2 dissociative adsorption to oxidize the nickel. We see that it's sensitive to crystallography and the defects. Also, we see that the like the opposite of what we think is actually the water prevents nickel oxidation and corrosion, which is a good news. And so there is this constant chemical transformation of the nickel chemical properties that actually tends to more nickel oxidation formation or more carbon coke layer. And so this is really linked to the reverse water gas shift chemical reaction that you see here. And so the next steps of this is to understand if the carbon coke can actually interact enough with the hydrogen in those conditions and actually trap the tritium and prevent it to migrate to the zircaloy 4. Sorry for the late. Thank you for your attention and probably your questions on the chat. Thank you.
Well, thank you for the presentation. We are a little bit short on time, so Stan is going to look in the chat for any questions. And we move on to the next presentation by Mainak Saha from the IIT in Madras, India. And the title of the next talk is Temporal Evolution of Nanoscale B2 Precipitates and Their Localization in Nickel-Alloyed Low-Density Steel, Iron, Manganese, Aluminum, Carbon.
Yeah, am I audible?
We can hear you. The presentation was briefly up. Oh, okay, here's the presentation again. But right now we see your
I'm sorry.
desktop.
I'm sorry just for a small interruption. So just a moment. Yeah. So
yes. Go ahead, please.
So good morning to all of you. So I would be talking on the temporal evolution of B2 precipitates, of nanoscale B2 precipitates. And just a moment. Yeah. So yeah, so I'll be talking on the temporal evolution of nanoscale B2 precipitates and the localization in nickel alloyed FeMnAlC low density steel. So, I'd be initially talking on the motivation and objectives of the present work, which have been as follows. That is, the material of interest that we have chosen is the hot rolled 5 nickel alloyed Fe16 manganese 9 aluminum 0.9 carbon, all in terms of 8% steel. So this kind of steel is basically a low density steel with a density of around 6.8 gram per cc, which is in contrast to the conventional density of, I mean, the mass density of the conventional steels, which is around 7.6 grams per cc. And the motivation of the work is as follows. That is, if we look at the variation of engineering stress as a function of engineering strain, we are able to observe that with the steels, with this FeMnAlC steels with nickel, these are the characteristic curves. The UTS, the ultimate tensile strength, is nearly around 50% higher than with a limited loss in ductility as compared to the steels, the FeMnAlC steels, which do not have nickel addition in them. So, now the question is, the very important question that arises is, why is there a strength ductility trade-off? And in order to address this question, the first approach is that we started with performing the thermodynamic analysis, and that we have performed using the TCF11 database of Thermocalc, where we plotted the variation of iron with 16 weight percent manganese, 9 weight percent aluminum, and 0.9 weight percent carbon as a function with different weight percent of nickel. And now, if we look at the 5 weight percent composition that we are dealing in our in this particular work, so we are able to see that the B2 phase is stable between room temperature to 1120 degrees. And hence we defined our objective of the work to be as follows. That is, the nickel-induced nanoscale B2 precipitation sequence we need to investigate as a function of the annealing temperature using 3-dimensional atom probe tomography, and also to investigate the associated B2 stability and its chemical composition. Now, the experiments were performed at 4 different temperatures. That is the room temperature, the 600 degrees, the 1110 degrees, all the 3 temperatures where the B2 is stable, and 1 more temperature where the B2 is not stable. And in place of the ordered B2, in that case, the disordered BCC is stable at 1200 degrees. Now, based on that, so let me move into the characterization part of it. That is, in the as rolled condition, that is at room temperature, as you can see, in the hot rolled condition, that is. So in the same EDS map, based on the same EDS map, what we can say is that that is the bulk scale analysis using the SEM EDS map, the gamma or the FCC phase is basically the major matrix phase, and based on this map, it is very clear that it is manganese rich, and whereas the BCC phase is the second phase, and this phase is banded in terms of its morphology, and it is nickel as well as aluminum rich, as you can see clearly from here. So as now performing the site-specific lift out from the BCC phase, so these are the elemental maps belonging to iron, manganese, aluminum, and carbon. But most importantly, what needs to be highlighted is that if you look at a proxygram, if you look at the proxygram corresponding to 4 atomic percent nickel isoconcentration surface, what we are able to observe is that there are the nanoscale B2 precipitates which are involved in a very, very localized fashion within the banded BCC structured regions, as can be clearly evidenced from the proxygram analysis. So, now exposing the material to a high temperature, that is 600 degrees, what we are able to observe is that we from the SEM EDS analysis, again, we see the same phases in bulk scale, but again, the site-specific lift out from the BCC phase shows the presence of, again, the B2 phase localized within the BCC phase, but now in this case, the B2 phase is slightly coarsened, and that is to around 5 nanometers. And the B2 phase now in this case shows a higher nickel content of around 23 atomic percent as compared to that of the AR condition. That is the previous condition that I just talked about, as old condition. So exposing the material to a further high temperature, that is 1110 degrees, again, we see that the same phases in bulk scale from the SEM-EDS analysis. But what we are able to observe is that from the site-specific lift out from the BCC phase is that the B2 phase is largely coarsened to around 26 nanometers, and the content of nickel in the B2 phase is further increased to around 35 atomic percent as compared to that in the case of 600 degrees centigrade. And finally, when we expose the material to a phase field where the B2 phase is not predicted to be stable, what we are ultimately able to observe is that experimentally that we still have, so in the case of the bulk scale analysis using the SEM-EDS, we have two phases, gamma and BCC phase. But the site-specific lift out from the BCC phase shows the presence of B2, but the B2 phase is observed to be disintegrated. Instead of coarsening, now it has got disintegrated within the BCC phase with a size of nearly around 6 nanometers, and with a nickel content which is lower, that is around 29 atomic percent, as compared to that of 1110 degrees centigrade. And very interestingly, it is observed that there is a 1:1 stoichiometry which is present in between nickel and aluminum, as we can clearly see from the proxygen here. So now to talk about the precipitate coarsening kinetics. So initially, so summarizing all the observations that we have seen for all the 4 different conditions using the 3D APT analysis, what we are able to see is that there is from the as roll condition to 1110 degrees, there is an increase in the size of the B2 precipitates with a concurrent decrease in the number density of the same. And when we when we expose the material from to a higher temperature, that is 1200 degrees centigrade, from 1110, what we are able to see is that there is the disintegration of the B2 precipitates when we move from 1110 to 1200 degrees centigrade. So so now the experimental results are also in very good agreement with the modified LSW model, where in which the R is nothing but the B2 radius that we have considered. The R0 is nothing but the radius of the B2 phase at time equal to 0, and that has been taken. And for all the other three conditions, the 600 degrees, 1110 degrees, and 1200 degrees, the R0 has been considered to be the radius of the B2 precipitates in the AR condition. And the K is nothing but the coarsening rate constant, and the T is the annealing time. So annealing time at the 3 different temperatures, 600 degrees and 1110 and 1200 degrees, which in this case is equal to half an hour, that is equal to 1800 seconds. So so based on these, what we can see is that the B2 phase coarsens with increase in coarsening rate from coarsening rate constant from as rolled to 1110 degrees. And similarly, and it is also to be noted that B2 coarsening is controlled by the matrix diffusion, as we can see that the growth kinetics is fitted with the modified LSW model, where we have the temporal growth exponent to be equal to 3, and also it needs to be mentioned that the temporal exponent for the number density is also based on these analysis, it was nearly equal to -1. And so based on both these temporal growth exponent and based on the number density exponent, the temporal exponent for the number density, we can say that the B2 coarsening in between AR to 1110 is controlled by the matrix diffusion. But however, we can also observe that a negative slope at 1110 degrees, I mean beyond 1110 degrees, indicates phase instability beyond beyond this temperature, which means that this trend is in very good agreement with whatever with the size, I mean with the variation of size of the B2 precipitates with temperature. So based on the observations, the conclusions are as follows. That is, the nanoscale B2 precipitates undergo coarsening till 1110 degrees and undergo fragmentation at 1200 degrees, but in all the cases, they're localized within the BCC phase. Secondly, the coarsening kinetics of the B2 phase is in line with the modified LSW model and is highly matrix diffusion controlled. And also, it needs to be mentioned that the B2 phase instability occurs at 1200 degrees, or more specifically to say that is beyond 1110 degrees, and this is very very good agreement with the thermodynamic estimates. And it also needs to be mentioned that the B2 localization within BCC in gamma-based nickel alloyed FeMnAlC steel leads to enhanced strength ductility trade-off. So with this, I would like to acknowledge my research supervisor, Dr. K.G. Pradeep, and also the other members of the team, and also all the other members for the National Facility for Atom Probe Tomography in India. And thank you for your patience. Now I will be ready for questions.
Thank you for the presentation about the NIL-B2 type precipitates in this lightweight steel. We can take one or two questions if there are any. Well, if there is no other question, I would want to ask Mainak, what is the intended temperature range for the steel?
Yeah, the intended temperature range for the steel basically is still 950 degrees. This is because in one of the literatures that I can show you, in one of the literatures that we can see, yeah, in one of the earliest literatures in the steel, the B2 phase is stabilized. So as we can see that the B2 phase is stabilized at above the gamma recrystallization temperature. So the gamma recrystallization temperature is around is around 800. I mean, is around 900 degrees. And generally, generally the B2 phase is the addition of nickel basically has been reported to stabilize the B2 phase above the gamma recrystallization temperature. So in terms of this is in terms of the fundamentals, but of course in terms of applications, if the question is based on more on the application part of it, then we can say that it is more likely that it is more likely that the steel is going to be used in the room temperature applications primarily, because they are being envisaged to be used in the automotive crash components. So automotive crash components definitely, because we need to have high crash resistance of this material, and for this we generally need a very high strain hardening rate, and then for that we need the B2 precipitates generally are non-shareable by the gliding dislocations. So in general, this increases the work hardening rate. Of course, they are not in application right now, but they are being envisaged.
Well, thank you very much. If there's no other question, we will move on to the poster session. In the poster session, we have 11 posters, and I'm being told that the way it works virtually is that every presenter will have 3 to 4 minutes to briefly go over their posters, and we will go in the sequence they are listed in. If a presenter does not want to present, we will just move on to the next speaker. So the first poster presentation in our list is by Jun Takahashi. Jun, do you want to go ahead and briefly walk us through your poster, please?
Okay.
Yes, we can hear you, and
okay.
Here's your poster. Thank you so much.
Okay. So. Okay, and okay, I am Takahashi from Nippon Steel. Okay, and in my poster, I discuss atom probability on quantitative analysis of nitrogen in steel and strange isotope effect. And okay, nitrogen is one of the most important RNA element in steels. However, atom probability on quantitative analysis of nitrogen in steel has remained unclear because of the mass interference of molecular nitrogen ions N2+ and matrix ion Fe2+ at 28 Dalton. And Chang first suggest 30 or 40% of nitrogen in steel is missing. And Shah report the mass interference is the cause of the nitrogen deficiency. And okay, so the objective of this study is to investigate atom probability on quantitative analysis of nitrogen by using a stoichiometric gamma prime Fe4N nitride consisting of nitrogen isotope. And by plasma nitriding using 40 nitrogen gas and 50 nitrogen isotope gas, 40 nitride and 15 nitride layers were produced respectively. And this is a nitrogen analysis result of 40 nitrogen in voltage mode. Nitrogen is detected as N plus and Fe2+ ions. The apparent nitrogen concentration was much lower than the real composition at 20 Kelvin and further decrease with the temperature. In order to avoid mass interference, 15 nitride samples was observed. And this is a nitrogen analysis result of 15 nitride. N2+ ion observed as a distinct peak at 30 Dalton. And however, even including the N2+ ion, the apparent nitrogen concentration was much lower than the real composition. This missing nitrogen increase with the temperature. The
1 minute left.
Okay. The origin is predicted to be the occurrence of neutral nitrogen or nitrogen molecule in the field evaporation. And furthermore, strange phenomena was observed. The generation rate of Fe2+ ion depended on the mass of nitrogen atom. The isotope effect was explained from the difference in the field evaporation of Fe-N atomic pair. From this study, we conclude that quantitative analysis of nitrogen is currently impossible. And okay, this is my poster. Thank you.
Thank you, Jun. This is a very neat experiment with isotopic nitrogen 15. Thank you. Our next poster will be presented by Heil Park. If the presenter is present. If not, we will move on to the next poster. Is Shebin Kormakal Jobi ready to present?
Yeah.
Then please share your slides or poster. Thank you.
Hello, everyone. Myself, Shebin. I'm a PhD candidate in Deakin University. I would like to thank my supervisors and APT&M for this opportunity. As you are aware, lithium-ion batteries have been using in portable electronic devices, electric vehicles, and grid energy storage. So in a lithium-ion battery, it works based on the shuttling of lithium ions from the cathode to anode, and vice versa during charge discharge. So when we go for high energy density, high performance safe batteries, there are several anodes and cathodes electrolytes were tried. So in addition to these electrodes and electrolytes, the interface between them plays a crucial role. The so-called solid electrolyte interface, or AIs, formed either at the time of fabrication of a battery or during initial cycles. So there are a vast number of studies done on SEIs. However, the 3D structure and composition of these SEIs haven't achieved at atomic level. And here is one of the mosaic model, but no atomic level studies were achieved yet. Here is the importance of atom probe tomography. And in our studies, we are using a next generation electrolytes based on ionic liquids, especially one from pyrrolidinium and phosphonium based ionic liquids with fluorosulfonide imide anions. So these electrolytes shows a better battery performance, and that's why we are using these ionic liquids based electrolytes. In our study, we are using a 2 electrode configuration to study the electrochemical studies on a copper specimens prepared using electropolishing and a platinum loop containing the electrolyte as the counter electrode. And then we are taking these electrochemically treated specimens for the atom probe tomography studies. Here we can see a voltogram with a copper specimens with lithium FSI and C3 empire FSI electrolyte. And we have taken this one for both untreated and treated electrochemically treated copper specimens for atom probe studies. And we have seen when for the pure copper specimens, there is a oxide and hydroxide layers formations and the apex of these specimens with almost 5 nanometer thickness. In addition to that, once we have done the electrochemical treatment, we have seen several peaks. Here is the mass spectra for the electrochemically treated ones. There are several peaks, including the lithium, and some of them we couldn't assign those peaks because of the overlap, and some's coming from the ionic liquids, some organic species, and we need to perform more experiments to sort out those issues. And we have done some more experiments, and it's on the way. So to summarize, we have achieved the atom probe spectra on an electrochemically prepared copper specimen with ionic liquid based electrolytes for the first time. And we need to perform more analysis to correlate these results to actual battery assays. These are the model surfaces with ionic liquid based electrolytes, and we need to perform the coin cell assembly or pouch cell assemblies to correlate these results with an actual system. So in addition to that, we need to correlate the SEA studies using atom probe with other characterization techniques such as SEM, NMR, and XPS, which are widely used to study the SEIs. And systematic investigation of alternate electrolytes and electrochemical treatments with these results. Revealing the 3D structure and composition of the SEIs can make a paradigm change in to fabricate next generation batteries. Thank you.
Thank you very much. Our next poster is presented by David Reinhardt. David, are you ready to go?
Sure.
Please show us your poster.
All right. Can you see it?
Yes.
Okay, so thank you, Dieter. Yes, so I'm David Reinhardt with Kamika, and I'm going to go rather quickly over our two new products, the LEAP 6000 XR and the Inviso 6000. Rob presented on them earlier in the conference, and you've also seen a few presentations on results from the Inviso from the Sydney group as well. So with this new product line, we have one new LEAP system that is built around the reflectron geometry and maintains the local electrode geometry, and therefore the microtip array sample system. But we also have the new Inviso 6000, which has a completely different kind of flight path and counter electrode geometry. So it is not a LEAP, and it is a single wire system only. So the main features of these systems, both of them are built around a deep UV wavelength laser system, so they share that and the benefits it brings. I will not claim to understand the laser physics, but what we have seen in our initial investigations is that we do see an increase in yield with the deep UV wavelength. So we have a test system, a silicon dioxide, silicon layered structure, which we have run many, many times on the 4000 and 5000, and now both of our 6000 systems. And what we tend to see is that there is much less variation in the voltage plot as you go through the silicon dioxide layer. So presumably there is some difference in the way the deep UV wavelength is absorbed by the silicon dioxide, which effectively makes the fields more similar between the silicon and silicon dioxide. So the voltage increases less when going through the silicon dioxide, and therefore you have lower stress on your sample and an improvement in the yield. That's not the only benefit we've seen with the deep UV wavelength. Because of this improved absorption in the silicon dioxide, we've also seen less of a local magnification effect in our reconstruction. So that same system, when we run it in parallel, we can see here the oxide layer in blue. In the UV system, we were getting a thickness of about 30 nanometers wide, and we know this layer is 12 nanometers thick from TEM imaging. And in the deep UV 6000 system, and we've done this with both of the INVISO and the LEAP systems, with just our default reconstruction, we're getting about a 15 nanometer thickness. So that's a substantial improvement, a substantial reduction in the local magnification. So again, both of the systems share the deep UV wavelength, but there are some substantial differences between the two systems.
1 minute left, please.
So the INVISO has an ultra wide field of view. We can get greater than 90-degree angular field of view, sometimes the entire specimen, depending on the geometry. So this lets you capture more of your sample. It lets you capture the edges of your sample. It helps with sample prep targeting. It also allows you to see more features in your sample, see larger features in your sample. The comparison here showing a lot more context of what kinds of precipitates you have and how they're arranged together. The INVISO also has 2 beams illuminating both sides of the specimen at once to make your heating more uniform and therefore your specimen more symmetric. The LEAP 6000, its unique feature is a simultaneous voltage and laser pulse. So you pulse both the voltage and laser at the same time so that your standing voltage between pulses is much lower, so you get less out of time evaporation and therefore a higher sensitivity, a lower background giving you a higher sensitivity.
David, we will need to end soon.
Okay. We are also able to improve the automation to completely handle the laser and local electrode and microtip alignments. So again, 2 new systems sharing the deep UV wavelength and some unique benefits between the 2 of them as well. Thank you.
All right, thank you, David. Our next presentation is by Jinyoung Liv.
I'm here.
David, oh yeah. Do you want to show us, walk us through your poster briefly? Hello, you can.
Oh, okay. Can you see my screen?
We can hear and see your screen. Yes.
Oh, okay. Oh, hello everyone. I'm Jinyoung Liu from China General Nuclear Power Research Institute. My poster is about the atom probe tomography characterization of anion elements in the colloidal ions after gravity formation. Field assembly is a key component of reactor, which is the important guarantee of safe, economical, and reliable operation of reactor. So the landing tube in the fuels can be said to be the first barrier. The colloidal ions, which has a low neutral absorption cross-section, high corrosion resistance, and good mechanical properties, have been intensively used as fuel landing tubes in nuclear reactors. The material combination is given in up chart, which is a new type of the column-tin niobium alloy named CD1, developed by China General Nuclear. Using APT and TEM, we observed the local chemistry of initial and gravity formed the column alloys to compare the distribution of annealing elements. The left two figures are TEM images of second phase particles. Through statistics, we can obviously know that the average size of the second phase increases after creep. And according to the results of the APT, we observed the iron, copper, and tin elements segregate on the green boundaries of the initial and creep from the samples. But tin element only enriches on the green boundary of the sample after thermal creep. Additionally, there are depletion zones of tin element on both sides of the green boundary in the creep deformed sample. From the above, we can draw the following conclusions. After creep deformation, the average size of the second phase particles increases. Iron, copper, and tin elements aggregates at the green boundary, and the tin element further diffuses to green boundary during creep. In the future, we will use in situ EBSD, in situ TM, and APT multi-scale analysis to dynamically observe the creep process to explore the dislocation moment and to observe the interaction between the second phase and the green boundary and the dislocation. This study is of great significance to clarify the creep mechanism of the column alloys and the dominant mechanisms of different dislocations under stress, and will provide theoretical support for the development of independent column alloys in the future. Okay, that's all. Thank you.
Well, thank you for walking us through your poster. Our next poster is authored by Yukiko Kobayashi.
Yes.
Yes. Yukiko, are you ready to show us your poster, please?
Yes, thank you very much. Can you see my poster?
We can see your poster and hear you clearly.
Let me start. My name is Yukiko Kobayashi from Nippon Steel. We have investigated the early stages of titanium carbide precipitation in ferritic steel, which is important for the precipitation hardening of high tensile steels. Although alloy carbides and nitrides have an NaCl type structure in stable phases, and they precipitate coherently in the ferrite matrix with a plate-like shape. Different morphologies have been observed in the early stages of precipitates. In the case of nitride, there is a consensus that the initial morphology is monolayered. However, that of carbides remains to be clarified. So, the objective of this study is to clarify the morphological changes in titanium carbide during the early stages of precipitation in ferritic steel. We prepared nucleation stage samples of isothermally aged models steel, which contains carbon and titanium, and the size distribution of titanium carbide were determined using atom probe tomography and field ion microscopy, respectively. In APT, the size and shape of precipitates cannot be precisely measured from atom maps due to large local magnification effect. So the equivalent volume diameter was estimated from the number of titanium and carbon atoms in a precipitate. In film image, lengths as the persistence lengths of precipitates along the tip axis can be more accurately estimated during the field evaporation by counting removed atomic layers of matrix. Then we compared the precipitate size distribution estimated by APT and film to evaluate if the precipitate shapes are close to sphere or not. From the observation results, when we compare the size distribution of precipitates determined by APT and film, almost the same distributions are shown in the steels aged for a very short time. This indicates that the shape of precipitates is close to spherical or cubical in shape, so precipitates grow isotropically. In the steel aged for a little longer time, size distributions determined by APT and film are different, which indicates that precipitate shapes become anisotropic, plate-like shape. In summary, titanium carbide precipitates in steel grow isotropically until precipitates possess approximately 5 atomic layers. This is equivalent to 1 nanometer of side length. Then, and subsequently, they develop a plate-like morphology owing to lateral growth. These results clearly distinguish the difference of morphological evolution of titanium carbide from titanium nitride, which start with monolayered cluster. That's all. Thank you for attention.
Thank you. We are moving on to the next poster, which is presented by Yinqing Wu. Yinqing, oh yeah, please go ahead.
Okay, can you hear me?
Yes, we can hear you.
Okay, wait. Morning, professors and students. My name is Yinqing Wu. I'm a student from Nanjing University of Science and Technology. My poster title is the study on segregation behavior of elements and grain boundaries in grain-oriented silicon steel. Firstly, as the most important soft magnetic functional material, grain-oriented silicon steel exhibits high magnetic induction and local cross. This excellent magnetic properties mainly rely on its gauge texture, and along the rolling direction is the easy magnetization direction. Therefore, how to improve the gauge texture has been the most popular question in this field. Up to now, many researchers results indicated that the sigma-9 gray boundary theory or high-angle gray boundary theory mainly used to explain the gauge grain growth mechanism. However, due to the limitation of the resolution of traditional characterization techniques, the theory lacks sufficient experimental support. In this experiment, FIB, EBSD, and APT method has been used to explore the distribution of elements and gray boundaries with different characteristics. Figure 1 shows the typical microstructure of silicon steel after primary recrystallization via EBSD technology. The mean grain size was about 21 micron, and this figure shows the typical gray boundaries like sigma 3, 5, 9 are highlighted by red, blue, and pink lines. All gray boundaries parameters are listed in right table. This figure 2 shows the atom distribution might and 1D concentration covers along gray boundaries normal of the 4 tip samples. From this figure, we can observe that the tin and nitrogen had observed segregation at all types of gray boundaries. In addition, the segregation of manganese is only found segregation at sigma 5, 9, and general high angle gray boundaries. So, in order to quantitatively and statistics the exercise of these elements, and we can see this figure that combined of these results, we can go to the conclusion that the carbon segregation and gray boundaries is less affected by grain boundary characteristics. And then the level of segregation of nitrogen depends mainly on the misorientation of the gray boundaries. And the lowest segregation level of tin at the sigma 9 gray boundary may be the reason for the higher mobility of sigma 9 gray boundary. This is my poster. That's all.
Thank you very much. Thank you very much. The
Thank
next
you.
poster is presented by Shu Kurokawa. Shu, are you? Oh, Yinjing, can you? Oh yeah, there we go. Thank you.
Sound is okay?
Sound is okay? Yeah.
Yep. So thank you for giving me a chance to introduce our little bit strange investigation today. My name is Shu Kurokawa from Kyoto University. So our investigation is the development of combination method of scanning tunneling microscopy and atom probe tomography. So this is a motivation of our investigation. So this is an example of a STEM observation of alloys. So this alloy has a very fine cluster as indicated here, and only STM can image that such structures in case of this material. So this result shows STM is sometimes very useful to observe the inside of materials. And STM need atomically flat surface for observation with atomic resolution. So such a surface can be made by cleavage usually, but the number of material amenable to fracture with atomically flat surface is very limited. So we think to use field evaporation to make such surface. So this is an experiment, and as you know, the sample of APT is a very sharp needle, and the STM tip is also a very sharp needle. So we need to adjust the position of STM tip at the apex of APT sample, and generally this is very difficult task. So in this study, we make many nanopyramids on the surface of tungsten 111 surface by deposition of platinum and utilize them as STM tips. And in this case, we don't need to adjust the position of the STM tip because everywhere we have a STM tip. So the nanopyramid made by this method has a single atom at the top of the pyramid, and this is ideal for STM tip. This schematic shows the situation of this experiment. The aspect ratio of the pyramid is very low, unfortunately. So we can observe the area of the 10 to the 20 nanometer in diameter by STM if we assume the apex of the radius of apex of APT sample is 50 nanometers. So this is a result of the our investigation. I show the result of tungsten APT sample. The sequence of STM scanning is A to E, and in the first image, we can see the same patterns in the yellow circles. These are image of single APT sample taken by different STM tips. In the next image, we can see the atomically flat terrace, and the quality of STM image is reasonable. Next scan, we found that some isolate were dropped by STM tip. And then we can confirm that the isolate also appeared in the another STM image obtained by another STM tip. From these findings, we conclude that we succeeded to image the apex of APT sample by scanning tunneling microscopy. So this is a summary of my talk. Thank you for listening.
Thank you for presenting. We have two more posters. Yang Zhang, there was one poster was cancelled. So the next presentation will come from Xu Zhang. Is Xu Zhang ready to present the poster? Hello, Xu Zhang.
Sorry, yeah.
Oh, yes, please. We still have time. We can hear you. If you want to show us your poster, please go ahead.
Sure. So I'll share with you my screen. Can you guys see it?
It's coming up. Yes, we can see it now.
Hi, everyone. I'm Shuo Zhang from Max Planck Institute. And today my presentation is approaches to prepare frozen hydrated nanoscale needles for cryogenic high resolution characterization. So firstly, I'd like to report three potential approaches for fabricating frozen hydrated needle specimen, needle-shaped atom probe specimens. So firstly, the open macrocapillary method. So we fabricate some macro patterns on the half-grid pillar apex or the needle tip to trap the liquid. And by changing all these parameters, we can partly control the volume that traps in. And then we just plunge freezing the liquid, the half-grid, to the liquid ethane, and then transfer the whole thing to the cryo for milling to fabricate the ice needles. Similarly, the second method is the high pressure freezing method. So the half grid is sandwiched between the two discs for high pressure freezing. And after that, we just remove the two discs from the half grid, and the liquid was trapped between the half grid pillars and also be trapped in the macro patterns on the half grid pillar apex. And then similarly, we just transferred the half grid with the ice to the cryo for milling to fabricate the ice needles, as we can see from this cryo SEM image. Is this cryo SEM image? And the third method is graphene encapsulation method. So basically, we use a single layer graphene sheet to trap the liquid on the prefabricated needle tip. So the liquid was like encapsulated between the like sandwiched between the needle and also the graphene sheet, and the graphene sheet can seal the liquid on the needle tip. So then we can transfer it to the cryo APT for like on-stage freezing. So we have conducted the cryo SEM diffraction for like and confirmed the vitreous state of the ice needles that fabricated by all these three methods.
You have 1 minute left.
Yep. And also I'd like to present another method called standout method. So basically, which just like the first step of the lift out method, which fabricate some freestanding nanoscale or macro scale nanowares from the bulk material, and then we just apply this ion beam irradiation at this joint area, and with the increasing and controlled ion dose, the nanoware will gradually stand out until the bending angle reaches like around 90 degrees. And finally, the specimen stand out. As we can see from these SEM images, the nanoware can stand out from the horizontal position to the vertical position. And then we can apply some platinum deposition on the joint area to like fascinate for the atom probe. So
we will have to end soon.
Okay, yeah. So we also tried this method at the cryogenic temperature. So in the future, we will try some cryogenic standout to explore the cryogenic applications to fabricate the to in situ fabricate the ice needles. Yeah, that would be it for my presentation. Yeah.
Great, thank you very much. These are amazing methods. Our last poster in the session will be presented by Tianyu Deng. Tianyu, if you're ready to walk us through your poster, please. We can hear you.
Yes, I will show the poster first. Can you see the poster?
We can see your poster, yes.
Dear scientists, scholars, and research students, my name is Tianyu Deng. My postdoc focused on the removal of pole and zone lines in the atom probe results of irradiated iron nickel silicon alloy. This is my postdoc. I will represent it in detail in the PPT. I will show the PPT.
Your poster was up briefly. Oh, okay, now it's coming back. Okay, we can. Oh, I see. Yeah, we can see your presentation.
I will show it in the PPT. This model steel alloy is irradiated with iron by 3 incident energy at 350 centigrade, and it formed a 1.5 dp platform. In this sample, we chose the 100 and 110 crater face from the A and B region in the EBSD map. Then the sample was run with these parameters in the deep 4000x. In this sample, the trajectory aberration caused by spaceman geometry near to the visible pole and zone lines. Pole and zone lines. As this pole and zone lines. The first nearest level distribution showed the existence of silicon and nickel clusters in the sample because the impairment count curve is different from the randomized count curve. And we use two methods to analyze the solute clusters. First is the maximum separation method. We use these parameters and we select 9 cylinder RIs. The 124 RIs avoid the pole and zone lines, and the 5 to 9 RIs not. Number densities and volume fractions was calculated in these RIs, and it's obvious that the results in RI 1 to 4 is different from the result in RI 5 and 9. It indicated that the ununiform distribution of silicon elements due to the affect the results of solute cluster analysis. For the reason, we use the algorithm combined with the HDB scan and high order KN to fill out the pole and zone lines in the sample. The parameters are listed here in the table to remove the additional data around the pole and zone lines. We chose the 4 cylinder ROI and the whole sample data as the ROI all. The number density and volume fraction results in these different ROIs are similar.
Tian, you have one minute left.
Yes. So the removal of pole and zone lines will lead to the uniform distribution of silicon elements. As a result, the properties of solute clusters are similar in these different ROIs. This research provides the techniques to avoid the effects of pole and zone lines when analyze the solute clusters, and it enhances the utilization rate of the experiment data to some extent. Thanks. This is my poster.
Well, thank you very much. This was a really nice collection of posters. We are concluding the session. It is lunchtime in Nanjing. Here in Chicago, it is time to go to bed, 11 p.m. So thank you again to all presenters for the talks and the posters. Thank you for the attendance, for listening. And I'm looking forward to seeing you in one of the future sessions. Thank you so much.